Aha, we're in. Right, welcome to Red. Welcome everybody. Thank you for that. Appreciate the heads up. Um, but yeah, as I was saying, hello everyone. Welcome to another stream. How's it going? So last stream I added a third acceleration structure, which is frustum frustum binning. Right, so frustum voxel binning. So Froxels for short. Um, because originally we had screen space binning in screen tiles, and then we did a BVH binning, right? And what we found out is that the BVH binning for the spheres ends up being slower to ray trace than screen space tiles for this very small test here that we've got. So what we did is we ended up adding, yeah, so what we're thinking about doing is adding an improved version of the tile binning, and having. Wait a minute. See, I explained it earlier, and I'll explain it again. I lost track. So effectively, the screen space binning has an advantage where you can optimize it based on a single view, which is from the view frustum, right? And the BVH has an advantage where you can sort of you can use it as an acceleration structure from anywhere in the world, right? So the thing that I'm sort of thinking at I think we're going to take so far is we'll have an optimized acceleration structure from the main camera's perspective, and we use for all other from all other positions in the world where we need to cast a ray. So maybe for some lighting, right? We'll use the BVH system. So we're trying to add a third one, which is which is hopefully an optimized screen space tile one, and this is a Froxel, Froxel based binning system. So as you can see, it's a little bit broken right now, the Froxel binning, but so I'm going to fix that today, and then we'll move on to prepare for doing some camera controls and stuff like that. Hey, they're not so red. Hey, they're Toaster man. Thank you. How we doing? Yeah, not doing bad. Not doing bad. Just had some family over. Had to stay over the weekend, so just been pretty cool. Catch up with them. Yeah, so it's been good. Been pretty chill. But yeah, I got like one more week left at work, and then I'm off. Off for 3 weeks, so I'm looking forward to that. Nice chilling. But yeah, how you doing? How's the weekend been? So basically, this is very hard to debug when you're seeing everything. So we're just gonna bring it down to one ball and just run with that. So we find the place where we generate our lovely dumbbell spaceship, which is here. We're literally just going to do this, right? If 0 and if else. And then we're going to take all of that, put it in there. And then we're just going to change the crap out of this. So, wait, do we have to change all of that? I could have just changed right, okay. So min, what's the radius of a sphere? Sphere radius. And then max would be, so negative sphere radius. And we might times this by like 125. And I want to make sure we at least emit one sphere. We have an insertion in that. Alright. Okay, we've got 8 spheres there. Maybe we can roll with that. I don't know. Let's just do the one sphere if that'll work. Shit, it worked. What's the step? Oh, it's half of step is the... Still though. I'm thinking, oh, that's cool. We don't have to be... Yeah, don't have to be working on one. Yeah, exactly. There's a refactoring to make the compiler work on Linux. Awesome. Right. Oh, we're inline functions. Right. Is it because the way they get declared or something? Oh. Like, like if you declare a inline function as static inline, usually it's fine, right? If it's in a header file. Right, we got a one ball. Excellent. Okay, so now we can debug our issue. So I think let's like talk about the problem and our solution. That we're trying to solve. Ah, strange. Are you using an MSVC compiler or is it Clang? Right, so effectively we've got a view frustum and we break it into, there's 7 depths, and essentially it's like the screen tiles, right? We essentially have a view and we break it into tiles, right? But it's got layers, right? And they're all even in real life, and there is actually many more than this. They're about 16 by 16 pixels on the screen, and they just go outwards. So they end up producing something like this, right? So the idea is that we need to, like, as you get close, as you go more to the left or to the right, the X, like, it gets wider, right? Like it gets wider, right? The further you go, the further your depth goes, right? And the more you go, the more your X increases or decreases, whatever way you look at it, the more your depth goes, the further it goes out to the left, right? And that's the same for the y-axis. The more you go up or down, the more it goes up or down. The further the depth increases. So the problem is right now is we've got a shader which goes over every single sphere, and it's simply atomic adds it to a bin, right? It just puts it into a bin. We have a two system pass where we don't bin it the first time, and we sort of take note of how many spheres went there, and then we allocate the arrays using a bump allocator, dead simple, and then we do it a second time and then bin it. There's ways to optimize that, but we just want to get it working first. So the problem that we're trying to solve is that we need to effectively select. So we only need to select a depth. I don't know what you call this. Like it's the column and rows for a certain depth. That's all you need to select when you're talking about a sphere. Then you need to select all of the frustum cells that it goes over, and in this case it's just here. But if it goes over like this, right, you only be selecting these two here at the front, right? Because when we ray trace from one perspective, we just need the closest place where it's going to hit, basically, that sphere. So the basic way we've done the logic is, so I think we'll just get to the code. All the functions C files and it's working now. Fair play. Playing. Also the weird bug where there's a variable after a label. Huh. Weird. Yeah, this sounds like a C23 thing that will fixes that problem. Where if you declare a variable after a label, yeah, that's actually like illegal C. But in C23 that fixes it. Very strange. Huh. Do you but yeah, I don't really care about inline functions much. In my projects personally because I typically just have them all in one executable, you know, and just sort of single compilation unit. But yeah, and if you use link time optimization, you pretty much don't have to worry about inlining either, because link time optimization will basically pack LLVM IR in those .o files, right? It would just be like LLVM IR, and then it's able to like inline everything because it's LLVM IR that it wants to. So inline functions are kind of like yeah, they're not really needed as much as if you have a bunch of core mass functions that maybe can be declared as inline, maybe that's right, but I usually don't care about it after that, basically. Because you just have a lot of stuff in header files, you know, and it gets a bit funny when you have to sort of like forward declare stuff as well. Ordering, yeah. But Froxel. Right. So effectively all we need is our left. We essentially need the index of the Froxel, or the x coordinate of the Froxel, the end index, the end x, and sort of like the start y and end y, and just iterate it over in 2 dimensions, right? We're looking top down right now, so you're not seeing the y-axis, but yeah. Yeah, I was just lazy, so I did everything in header files, and it was good. Opportunity to fix that. Awesome. Nice. So the way the code works, let's just have a look. Yeah, so I think the way the code works is we get our furthest left point. Yeah, essentially we build a bounding box around it in a sense, but we don't really care about the back piece. So we've built a bounding box in 3D, we don't care about the back piece. And then we get this furthest left point, and at this depth, right, the near depth, we find that point there. And then we essentially get on the near plane, we get the width of and the height, mind you, separate variables, as of the tile in screen space, right? And then we project that out at this depth, right? So we know the width. So basically, we know the width of a Froxel at this particular point here that we've got our thing at. So what we can do is we can basically do a bit of maths, and this is where it's probably going wrong, to figure out, like, this is x-axis 0, 1, 2, 3, right? So bear in mind, like this, in terms of coordinates, this here is at 0. So, and then going from the left here is into the negatives, and going into the right is positives. So essentially we figure out, we just do some maths to like basically calculate that 0, 1, 2 or 3 index on the x and the y axis, with this left position and, you know, the right position, and sort of able to iterate over those. So actually, that's a poor example. We've had a sphere like that that went into both those cells. That would have been there to there. But anyway, so let's just quickly go over the maths and see if we can fix it. So Right, so what do we got? Okay, this thing that we use, what is this? Froxel dims near clip space. So it uses the Froxel XY size, so that's it in screen space. I should have said screen space with this. Right, let's correct this. Just correct all of that lovely. So it's just easier to read and understand. So, go back to that calculate counts. Right, so we get the screen space times by pixel and near pixel size and near clip. Plane. Yep, so that brings us into near clip space from screen space times by the aspect ratio because the width is larger than the height. Right. Okay. Right, there's something to take note. Is the way the tiles are laid out on the screen is the middle is not directly on a, like the middle of the thing of the screen is not on the sort of edge or between the, it's not on the crossroads between like four tiles, right? So is that a problem? Because really up here, you know, so we've got to be aware of that. I think that could be part of the problem with calculating some of the stuff. Because we're relying on the fact that dead down the middle is, yeah, sort of like a 0, 0, sure. Yeah, I think that would be a bit problematic. Well, we haven't defined the screen tiles as being that in any way, as coming perfectly from up here. We've not done that. So I think the way we're defining it here is in fact defining it so it is going to be that way. So we just got to remember, yeah, okay. Okay, so into account. So this is the dimensions of a Froxel and near clip. Do we end up using this near clip plane width? We didn't, did we? Okay. Interesting. Right, so how do we go from here? So we move our sphere into from world space into view space, but we still need to do that obviously. Then we get the furthest left position, furthest right position, furthest bottom, furthest top, and nearest. But we don't care about the furthest point in depth. So you got the dims at depth. So it goes from the near clip space, multiply it out to take it to the right. All looking good so far. So we've got Froxel dims at depth. So we've got this guy here, this line here, right? And obviously going up as well. This is looking top down. So I think that's looking good so far. So the min x left divided by, wait, why are we dividing? Froxel dims at depth. Okay. Right. So if we're one of these dimensions to the left, it should be -1, right? Because this would be negative. So if we're one of them to the left, it would be -1, meaning it'll start there. And then but anyway, we floor it for anything sort of close to that. And then we add Froxel dims or grid dims. So this is saying, oh, you've got 4 going across, right? So you're saying, okay, increment by 2. How's that number calculated again? Divide, round up. So that could be odd. So it's odd what happens, basically. So if you got like 5, right? Then obviously this isn't going to be in the middle anymore, is it? So essentially you're going to have you'll go through like halfway through one of these instead, and then when you say you give one a whole one to the left, right. So if you're just gonna hold one to the left, and probably something like the line would be here or something like that in the middle instead, and you would be. Say if there was 5 of these. You would go to the left. Sorry. Yeah, you try and put this in here. You go to the left and say, okay, mine starts here. This is 0, this is 1, but in this case, this would be... but in terms of how this works right now, this would be 1, 1.5, 2.5. Right? This obviously just be a half here. So then so if you've got like, oh, I'm 1.5. Wait, okay, initially you'll just be, you'll put your thing in. Well, it's not gonna be a half because you can get Lord, isn't it? So let's go round it back to. Let's get round it back to 2 here, wouldn't it? Whoops. Yes, as if you've got to. So you'll get rounded back down to 2 when you do your sort of like. So you'll have. Oh, my furthest left point is. It'll get rounded back to somewhere like here. It's a bit of a problem when it's odd. Maybe we can just make it even, and then that fixes some issue with it. Because otherwise you get these sort of halves here instead. It's going to snap to, rather than the actual. Let's think about it. So this would be like negative 1.5. You go back to 2. So it'd be somewhere like there. And then if you say add half of that, so you'd be adding 2.5, right? So you'll go from 2, minus 2. Then you add 2.5, you're then on to about 0.5 over. And then you have to 0.5 over, so this is to be 0, this is 1. So you have to round it up in that case. You have to be a round up for the odd. Does that make any sense? Unless we can just make it, if we make the problem, like if we just have an odd number of x or y's, we could just add a yeah, maybe that's fine. Let's just follow that through. So you'd have gone, right, so we did this case here. Let's put a sphere here. We would have got the left-hand side point, which would have been 1 to the left, 2 to the left, rounded back down to 3, all the way out here, which would be outside, right? Then you do like, essentially, you're adding 2.5, right? Which would have got you to 0, minus 0.5, then you round it up, right? The nearest one. So you always get off by 0.5 when it comes to an odd number, I reckon. So let's do this one here. This is yes, your furthest left would be here. So it'd be rounded down to this one, which you get your minus 1. So add in half of the number at the width, so it's 2.5. So minus 1, so it'll be positive 1.5, right? Yeah. And then we round it up, which will get us 2, which is right, because that'd be 0, 1, 2. Right, okay, so that does work. So if we have an even number, then the line is directly down the middle. Then that would mean, let's just do it again quickly. So you get your furthest left point. So that'd be negative 2. Right, you add half, which would be 2. Or you add half, which would be 2, right, because it's 4, and that'll get you on 0. And then you round it up, right? And then that's obviously just going to be on 0 again. Now you could get absolutely buggered by epsilon with this. So you got to be careful. So if we nudge it by 0.01, then do like a round operation, it would be better, right? Rather than doing a seal, I think. So in terms of this has to be a floating point. There's no way around it. And then you're adding that and then doing a round. Sorry, you're adding that. Sorry, doing that. Plus the 0.01 to then all in all do around F32, right? And that should be the answer. But if it's the max, does it have to go the other way? But if it's the maximum side. No, it's probably still around, it's the same deal. I'm not sure. Let's put these all on the end. And we'll see in a second. So it's up, that. Right, so the other check we need to do is say like, okay, well, the maximum point, in this case here, which would have been, all right, imagine I've got this fifth one. So your line would be in the middle, your middle line would be here. Damn it. Whatever, your middle line would be there. And so you've got this, which would be 0.5 to the left. You add in 2.5 because it's half of 5, and that lands you at 2, right? Wait, sorry, you're minus 0.5. Yeah, it just lands you solidly at 2. No, sorry. Excuse me. This would have got rounded up because it's seals. Yes, that would have been rounded here to 0. Then you'd land on 2.5. And then you have to round down. But you don't want to get screwed by epsilon, so you need to take it away instead. Okay. Right, that ought to be it. So that's a fix for if this is an odd number. These grid dims. So a number of width or height on the grid if that's an odd number. So let's keep trying to fix some stuff. So we could test that out, but I just want to double check some more of the code. Just in case there's anything painfully wrong. Froxel Z. So the Z is just the nearest depth, log 2 of that, because we're doing log 2 steps. I'm not sure if that's a good idea. So it just means that the ones at the near are going to be, we'll have like 1 or 2, have 1 meter for the first cell, then we'll have 2 meters for the next cell, 4 meters, 8 meters, 16 meters, 32 meters, 64 meters, 128 meters, 256 meters. Something like that, right? So something's a little bit off with that actually, I think, but we'll look into that a bit. But yeah, so that just does a so you bring that down into log 2 form, right? So it'd be like 0 to 7 or something like that, and then we clamp it in between there. Looks good. Loop over all the X and Y's. Calculate Froxel index and roll from there and bin it in those X, Y dimensions. All right. Let's take that for another spin, see what happens. I need to move this over to the other, because again, we do it one pass to calculate the counts, then we allocate the Froxels with a bump allocation method, right? Very simple. Then we do the same thing again and actually bin them properly. That code's different there. So again, we could probably make that better in the future, but for now, let's just roll with this. Okay, so we didn't really fix anything. So there's still something painfully wrong. But I do. So first thing I want to check is is it an odd number? And then we can as we get more to the left, it obviously cuts off the right and vice versa, right? And the up and downs as well. So something's fishy there. Like we're being cut out. So I don't know what we're dealing with really. So let's just quickly check those grid dims. Right, these boys. So something like core debug Yeah, call print basic. Wait, I think we did print strut. No, basic would be easier. Sorry, what is it called? This one, isn't it? $x would be another one for a y. Right, so if any of those odd numbers, we'll pay attention to that as well. Right, 60 and 80, so they're not odd numbers. That's not is what's going to be causing the problem at all. So as your multi-right cuts off, it's as if it's not paying attention to the depth or something like that. It'd also be nice to kind of visualize the it would kind of be nice to visualize the screen space tiles that the Froxels come out from, right? And we might see things better. So should we work on that visualization? So we go to the tiled ray tracing. There's probably some debug code in here to do with that for the tiles. No, there isn't. Oh, it's in the yeah, we've got to do something a little bit different. Right, let's just take something like this. Not here, you want to search for HSV. Yeah, something like that. So, if we go to that Froxel ray tracer, where it goes in through the Froxel acceleration structure. So when we come into here and do our ray tracing, what do we want to, like, I think if we want to render something if we don't get a hit. Because then we can just see all of the tiles, right? And then we can still see the spheres on top, right? So we don't get a hit. So we can do like a if 0 for now, and just enable it when we need it. So just do if we don't get a hit. What we're going to do is we're going to work out using that same logic in the calculate bounds stuff. Sorry, calculate counts, the Froxels. We use the same method obviously to color this. So they each can get a different hue. So we need to find out our Froxel index. So how do we work out our, well, it's our tile index, isn't it really? So if we simply work out this min x, min y, this is what we need, is Froxel grid dims. So I need something like this stuff here. Right. So let's just get rid of stuff until we so I need some of these variables passed in. I need some aspect ratio in here as well. So let's get some aspect ratio in here. And we'll need, so we don't need the sphere, right? Wait a minute. So we've got a screen space pixel. We just need to know what tile we are in based off from the middle of the screen, basically. It might be able to work a bit easier. Maybe you just need the grid dims and how big it is in screen space. We don't need all of this stuff. Thinking about it. We just need Froxel size screen space, and we just need how many grid. So we need how many grid dims there are. So if you just have the width of the display output dims, you could just roll with that, right? Now if it's an odd, so we just want to work out an x, y, and then throw that into like a hue, in as the hue or something like that. So we'll work out some form of like tile index, and that'll just be like, we still need this grid dims though. So work out the y coordinates. It's dot y divided by this guy. These are both integers, right? So things will kind of get rounded down, which you've got to be careful about, because if it's something like, yeah, if this ends up being, okay, if this, wait a minute, would this ever become, oh no, become an odd number, that's fine. Yes, if this is an odd number, then we kind of want to have it off-centered a bit. Like, if it's an odd number, then you're basically in the middle of a tile. If it's not an odd number, you're on the edge of a group of 4. Or not a group of 4, whatever it is for the axis rate, basically. Like, if the x is an odd number, you'll be somewhere like that if the y is an even number. Why is that right? No, you'd be somewhere like that. And the other way around for the other. Vice versa. So if we divide the size of the screen divided by how big a tile is, that'll get your tile like, that tells you how many tiles fit in, isn't it, really? So it's just this thing here, which we've already got. Let's divide it, round it up anyway. So we can just use that. So we kind of need to know, given our pixel coordinate on the screen, what sort of one it ends up in on there, but it's going to be, probably got to offset it. So it's U coord, right? So how many times does this fit into that? So that's a pixel position on the screen. So you want to do wait, no, it's the grid dims. Wrong one. Yeah, that's the offset. Then you want to multiply that by the number of cells on the x-axis, and then add the result of that from the x-axis. Now the problem is if this is an odd number, you need to apply some form of offset to this. Yeah, but that's why it's an odd number, you need to add an offset. If the x or y is an odd number, you need to add probably just a 0.5 to the result, so it'll round up. Well, it's going to truncate anyway, isn't it? So you just need to add a whole 1. So something like, you know, if that is not even, right, you just want to be doing that. And that'd be floating point, and then you just add the offset to the result. Wait, do you care about the floating point? Not really. Hey there, Perry. Happy Sunday. How you doing? How's it going? How you been? Happy Sunday to you too. Wait a minute, what are you adding it to? Do you add the whole one to... No, you kind of want to add half a... one of these guys, half of that. Something like that. And you add this. That'll do it. Okay, so get your tile index. And from there we can throw that into the hue generation thing. And that should... We really got to test this out being an odd number and all. We can do that by flipping the boolean. So hue, saturation value, this guy, get rid of all this code that we thought we needed but we didn't. And that should give us some color. No. Are we using Wayland yet? No, not yet. No, 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 no. Ah. There's a tile index in my face. Interesting. The Froxel ray trace at the start is generating a tile index. So that could be wrong. Hence why, so it might not be the binning that's the problem, it could be when we're ray tracing through, we're selecting the wrong one. Yeah, one day. I'll tell you all about it one day. But it won't be for a while, Perry. I'm not sure when I'll do it. Like, unless it becomes like... Yeah, unless it's like... You know, until everyone's switched over, then I'll move over for it. But I'm not really in any rush. I know, like, most people... You know, all the Arch fanboys moved over. But I'm not... I'm still skeptical. Red Hat is dropping X. Wow. Yeah, it's just the Nvidia thing's the problem, right? But as soon as that's all sorted out, it'll be good. And yeah, I hope my input stuff still works. Can you believe how long it's taken though, Perry? I remember when it was close, like 10 years ago, how we were getting close to Wayland. Literally 10 years ago, so long. But it did seem like it mostly worked though, for me on my hardware. I just didn't really try extensively though. Two or three person job to maintain X at the moment. Interesting. At Red Hat. Probably not doing too much development on it. So let's just call this a sort of like D-tile for some reason, because it needs a D in there. And let's see how it looks when we render it. Okay, so there's our tiles. That's a lot of bloody tiles. So you can see where it's cutting off, right? It feels like it might be off by 1, but I'm not sure. That's more than 1 tile it's off by, isn't it? It's the left and the right that's a bit buggered. Oh. Yeah, we are getting it perfect on each side though. So let's introduce a bit of should we introduce a bit of like if I do something like that, will it introduce an offset? The correct offset. No. So we work at that Froxel. Yeah, so it's divided by 10. Wait, divided by 24. Right, that's a bit of a. So it'd do a round up though, wouldn't it? So what's 32 again? That was an even number. Right. It's all gonna be even. It's gonna be even all the way down to about 10, isn't it? And then 5. Damn it. See, what about 48? Round it up, that'd be 27. Okay, so if we make these 48 big for a minute, just to see if it's right. Hopefully it doesn't blow anything up. Okay, so the way it's done this around the edges is not right, right? This has been off, like we want it to be, like this should be hard, like whatever it would be, like 1/66th of a tile or something, whatever it is. So I thought we had this thing called an offset. Like, what is that doing? Right, fair play. But yeah, you looking forward to Christmas, Perry? You got got any time off? Uh, maybe it should be a half. That's looking better, I think. Where's the middle of the screen though? I cannot tell. Yeah, finish the 17th, something like that. I'm off all Monday, Fridays for the rest of the year. Nice. Mondays and Fridays. Double dip in there. Cool. Me and okay, fair play. So I'm off from the 11th. Thankfully, because I had the paternity leave, so I had some fair few holidays to kick in. But I was hoping to save more of them for February when I go to Australia. But so what I've ended up doing is only carrying 5 over. I was hoping to carry over 10, but anyway. So I've got a whole extra week off for Christmas, which is still good. Um, so I'll just be chilling, basically, seeing family and relaxing. Um, Boxing Day, I'm going around my mum's or my parents, basically. Christmas, gonna go around my one of my wife's family members, and then Christmas gonna see my grandparents and my parents again. So it's pretty packed. So it's gonna be good. Probably eat tons of food, you know. But yeah, that's about it. Um, but yeah, it's the baby's first Christmas as well, and he's gonna know absolutely nothing about what's going on. So but it's cheap this year, which is great, thankfully. Save up for him next year. Yeah. Uh, hmm. Little bit curious on what's going on here. Does that change the shape of the... It doesn't. Okay. I think I need to open this up in Krita and see if this is correct. Oh, then you have to open it up. So this is... It just feels a little bit offset. It's not good. Like, I was expecting that to be in the middle. No, but they're 48 big. There's an odd number of them going across. I forgot what the number was. Um, but in terms of the debug, we need... If it's an odd number, we need... Huh. So we made it not an odd number, let's put it back to 16. How's we looking with something like that then? Let's do a perfect rectangle. So we should be on yeah, one of the edges, right? It's going right down the middle between two of them. And right down the middle between two of them. Right, that is fine. But when it was a number like 48, where's that number divided by 48? Which gave us 26.6. Tiles going across, right? So we need to basically have... Well, we could align it where it goes directly through the middle of them all, and that's probably the better approach to take, actually. So how would you do that when you do this debugging? So if you didn't have any offset, done all the babies shopping. No, we're not really thought about anything for him just yet. But he just needs stuff constantly buying from him. Like he needs more clothes still. I'm sure we'll hopefully get some clothes from people as well. Like here's the baby clothes, but yeah, like not sure. We might get him. Like he's not into toys yet, but we might get him another. I guess we might get him like hmm. Yeah, I'm not sure yet. Is that one directly down the middle? A little bit weird. No, it's not, you see. So it's as if we need that fraction that you're off by. Like we want to move it so this. Bit curious. So we can move it to the point where it's directly in the middle of this thing and it's like a 0.5 off. And we did the maths for that already in the other shader. Or we can move it directly onto this one, but in that case this will go forward a bit and you get into the negatives there. That's not won't be good. Yeah, so what is it like to move it to there? That's 48 a tile, right? So we do mod that was percent, so that didn't want to work. Mod 48. $32. Yeah, so I guess you would do something like then 48 take 32. And then you would do you're probably just 16. You're 16 away from the edge. So which is the best way to look at it? So you're 16 away from the edge. And you're 32 away from the other edge. So you're 16 away from the left and you're 32 away from the other edge. You want to get in the middle in this case. So I guess you just do so you kind of want to get this number, then take this number. No, which number do you want to get? So you're 16 away from the edge, so you're about here. You want to get to the middle. Like you need to apply some form of Hail Pill. I make an attempt at programming language again. Cool. C equals lacking, C plus 2 blurred. Yeah, I don't know. Yeah. It's C is kind of good enough, but yeah, it could definitely do with a cleanup though, I can agree with that. So the middle is 24. Right. So you kind of want to get to the middle from whatever your left is, I guess. So you just do 24 take how much you've already moved over from the left, and that's how much you go over. So that's how much you need to offset everything by, is that number. So it was mod Okay, so you've got 48, which is this thing. Mod that with the output dims. So it's something like this mod BC output. Oh no, the other way around. What am I doing? BC output dims X. Right. So you like 16 or whatever. So I got you 32. And then you need to do like that, take away, like just 32. Take away the 48. Right. That gives you 16. There must be a better way of doing this. Because you've got to go towards the right hand side. Nah, it's probably not. There must be a better way. And it's that divided by 2 plus that. Basically. Probably a better way to work that one out, but let's just roll with that for now. So that's how much you need to offset it by, so you no more multiply anymore. So yeah, could be simplified. So we try that out. Yeah, definitely. Yeah, get rid of the replace the includes with something better. Hey, I'm campaign. In left, take it right. Get to the center. Right. Yeah, I'm just trying to work how much you need to offset the screen by based on the tiles. But yeah, it's a good point. If you have 2 points, you can get the middle that way. But between 2 points. Oh. Wait, between 2 points. But yeah. Yeah, I'm not sure that's the exact problem though. Right, I think that seems to be in the middle. Now let's put a rectangle around it and we'll see. It's not, is it? Here. No. No. So mod 48 gave us 32. So I was trying to work out like the... Oh wait, I did this wrong. Yeah, so 32, 42, 32, 16. And then it's going towards this as a takeaway. I think that's it. If we redo this, it should just do the rectangle. Yeah. There you go. This has dead down the middle now, you see? If it's an odd number across the X, it will be down the middle of one of them. If it's an odd number across the Y, it will also be dead down the middle of them. Excellent. But if we put it back to a sensible number like 16, this should be... And hi there, I'm Campaign. How you doing? Welcome, welcome. This should be a... Oh, I've got to draw it again, because I closed the program. Right, it's dead down the middle of those as well. What is going on? Oh yeah, we only want to do that providing that. But we can always... No, we only want to do it that way if this is an odd number. Or we can make it always work that way. I feel like there's a better ways to do this. But yeah, it feels like we definitely get more than a but yeah, we sort out the tile, so I should debug that properly. But it feels like more than a tile taken away, put it that way. Well, if we up this to 46, we might be able to see it. Well, no, we're not more than a tile taken away. There's something more to this going on, though. It's not... Yeah, the tiles are not aligned to the screen, actually, just yet. But yeah, I might keep it on... Yeah, we'll come back and look at 48 when we're properly debugging it, but... So the problem that we're trying to solve, right, is, you know, it's fine. Like, for an even number width, like, you're directly on, your middle of the screen is in between, right? These guys, which is great. Because the way you can sort of work out the X and Y position is a lot easier, I think. Is that right? Yeah, but as soon as we have an odd number, it would introduce a problem where the middle is actually directly down the middle of one of these guys. So that's why we had to line it for the debugging, right? Is that it's directly down in between two of them instead, which is problematic. Well, you have to account for it when you calculate your Froxels are. It's a little bit, it's off by 0.5. The debug visualization has to account for that. Like, otherwise it's going to be like, it's sort of aligned from the top left hand side, which is not correct. So have it going directly down the middle, it's just easier to calculate that way. Is that right? Yeah. So there must be a bit of maths to sort of like... Yeah, because this is taking the actual Froxel size into account. There might be an easier way to do it. Say if you got 5, right, going across. Right, you just need to add 0.5 of this size, which would have been 48. And that could have just been... Yeah, I think it... Didn't we have that before? Wait, let's back this up 2 seconds. I swear we had that before. And then it just wasn't right. Yeah, it was right here. So So we said, hey, if this thing is an odd number, then multiply it by the half of this, which would have been 24. And that offsets the coordinate before you... Let's see where that was wrong, because I can't believe that would be wrong. So for this one, it would just be fine. Because it's 16, it doesn't need it. So just go directly... Yeah, if you just correct that a little bit. It's perfectly fine, right? It goes directly down in between two of them along the X and the Y. Perfect. So we keep that open. But we made it 48, which ends up making an odd number of cells along the X and the Y. What we'll find is that it ends up being off by a weird amount. Oh, I shouldn't have pressed escape. I should have taken the screenshot. Damn it. Seems to be off by some weird amount, but I thought we had the offset thing taken into account here. Yeah, so it's 16 off, and this is why we did that complicated thing. Just didn't make too much. It was actually only along the x-axis. This one's perfectly fine. So the x-axis is off a bit. So for this one, we want it to be aligned in the middle because it is directly off. So there is, what was it? Divided by 48. There's 26.6666 whatever cells along the x-axis. So because it is an odd number, do we need to take it away? We need to take it away from something. Like, surely we just need to take away the half. This is like 24 or something like that. Yeah, so if it's an odd number, the offset would be like 24. So maybe we need to take it away before we divide it. Let's try that and see if that's down the middle. Right, we're getting a bit of duplicate there. That's not good. Or there's something dodgy there. That doesn't look even. Yeah, that's not right still. Yeah, because I would have underflowed, I think, and made it a bit dodgy. We're adding the offset too early. That's the problem. It needs to be added after, and we might need to clamp it now. We might not need to clamp it, to be honest. Right, that's definitely the fix. I can see it. No, it's not the fix. Why is that not? Right, integer. Wait, you added 24. Why did you need to add 24? Yeah, so So U chord divided by, that's the screen pixel divided by 48. That tells you sort of the, oh, maybe it does need to happen in to this. Well, yeah, it could happen either or. It could happen after or before. But if it happens after, it has to be in floating point. Um, so we don't have the, let's go back to this one. So we saw that was like 16 off. We needed to be like another 16. Another offset of 16 there for that particular piece. Right, so I guess we want to round it up to 27 and then get the division of that. Oh my days, that's probably the issue. Is I'm thinking it's 26. Yeah, so we're actually getting 27. So it should just be 27 divided by 2, and that would be... yeah, I'm thinking... Oh. Okay. Something like that then. Okay. So it's because we like rounded up from 26 to 27. So this is actually 27. That's fine. Yeah, if that's an odd number. So we can't simply do offset by, right. Yes, it is kind of right going down this route, I think. Yeah, I don't think we can get any more simple than... yeah. So they might have to just do something like this for now. Maybe there's a better way to do it, but... For now, this will just work. Okay. There needs to be a dot y there. Rightio, so... That'll be directly down the middle now. Because it's odd going across. Whereas this one is even going down number of cells. So it goes directly in between the two. And then we bring it back to being even all around. Obviously, they're just going to be directly down the middle, in between. Yeah. Okay. So now I've got the debug tiles sorted out. Let's move up to bigger tiles like 48. because the best thing about this number, even though we're not going to make it 48 in size, our screen tiles, is that along the x-axis is even. Sorry, on the x-axis is odd number of cells and even on the y. So we've got that sort of, we can debug those bits of code. So, right, so it's kind of, it's not clipping as bad. So on the y-axis, where it's, okay, so where it's odd, you get this really weird clipping, like that, first of all. But when it's on the even number of, right, you're getting a bit of a weird clipping here, like, but never by a whole one. And it happens like, yeah, as you get further away. All right, so I think we could probably investigate. Right, so let's go back to where we calculate those sort of counts for the Froxels. So in particular, yeah, it happens when we go up and down. It clips the Y right at the bottom side. So it feels like the far depth isn't being, like we're not taking into account the far depth, right? But I feel like that could probably be an issue where it helps. So let's go back to here. Yeah. So near the edges of the screen, it looks like this. This point here, which is furthest, like, to the right and furthest down, right, is actually the y-axis. Sorry, yeah, so when it's furthest to the right type of deal, along the x-axis, it's the furthest to the right when it's at the back of the sphere, but not the front of the sphere. The front of the sphere will probably be around here-ish, right? So I think we're taking into account of that thing. So when we take into account the furthest, wait a minute. Yeah, I've got to be careful here. This is down projection. Yeah, so ideally the furthest to the left or the furthest to the right really needs to actually take into account from the... No. No, it's the same. Dims at Froxel. Sorry, Froxel dims at depth. So at this depth. Where's the X? Yeah, because the way we're working it out should be fine. We don't need to divide by depths anywhere. Because a near depth, we multiply that out to there. It's only building the box at the front. Yeah, it's only building the access line bounding box at the front. Could that be a problem? it's building the bounding box. What can we do to check this? You've just got a sphere in the world, right? Let's get rid of that. You could get that sphere in the world, which is not going to be distorted like this view frustum is, right? So you put your world space bounding box around it. And you get your furthest left point, and then you round that down to the nearest. Like you get your... This is your... We work out the width of a Froxel at this depth. We get the furthest left point rounded down. This is your min, Froxel x, and you get the furthest right and round it up. That's your max Froxel x, right? I don't see any the need to care about the back with this sort of the way this works, right? So I'm curious why that would be a problem. Yeah, why would that be a problem? So when you go up, it starts clipping off at the bottom. It's like which is where the far end is, right, of the sphere at the bottom. So, is there anything else we can do to sort of, we can run these numbers in the ray tracing shader. Could we? Okay, we've hit the sphere. We could get the sphere that we hit, and we can calculate the Froxel min and max, and we can just bring those up and color those in instead. So that could be something else that we do. So in the you need all these things though, wouldn't you? Yeah, so we could just literally do all of this. So we go to Froxel. I've still called that damn thing Froxel. Right, let me just quickly do this spelling thing. Such a weird word to type. Alright, we're back. So, anywho, something about taking all of these, and in that Froxel ray tracer, so we ray trace with the Froxel acceleration structure. When we do this, we'll do another if-def, right? Basically the same sort of thing. What I want to do is I want to disable the other one and bring this all in there. What we want to get is a hit. The sphere that we hit. Do we have any idea of what that is? First it says if we've not found it here. Right, we found it here. Yeah, but it's not going to color in the... No, we're just going to run this all the time. This is a very temporary thing that we'll have. We're just going to do this. We're just going to grab the first sphere, because that's the only one that we're debugging. So with this one, so you need the aspect ratio, let's get that. And we're just going to draw all of the Froxel spheres. Right, that seems to run, or compile, which means it's guaranteed to run, right? So you've got this min x, min y. Where does the U chord fit, like the pixel that we're drawing? like we want to know X and Y. Yes, if our tile index, right, it was a tile XY. Yeah, that's an interesting thing as well, as our Froxel start and end could be off. Yeah, this is probably actually off when we ray trace, so that's part of the problem. This is probably the issue actually for one of the problems that we've got. So then we've got two issues to solve. But anyway, so we want to work out this sort of coordinate. Okay, so that's divided by that, and it, so that should be whatever this is. So before we flatten it, basically. Something like that. Okay, so we want to say if we're in between these guys, then render this color. We'll render this background out. Did we only want to do it if we didn't do it here, actually? Yeah, saying that actually is probably do that. So saying, okay, if Froxel min x less than or equal to that, and the y version is less than that, and keep going. Yeah. And the Froxel max x is greater than, and the Froxel max y is also greater than that. And then this should mean we can store this out. That color right there. Right, let's take that for a spin. The color we're looking at doing is, oh, you want to flatten it. Do another one of them as well. Right, see how that looks. Okay, so now we're seeing the Froxels that are actually being referenced. Or the tiles for the Froxel. But yeah, so if we go up, you should see when it cuts. Yeah, it cuts it off right there, see? Okay, so we can see it actually being cutting off. That's really good. The X1 is off though. Yeah, anyway, so we're seeing it cutting it off. So we can see by this, we can play around with the way it's sort of working out the min and max here, fix it, and then take it back to the other shader, I reckon. And that will fix the Y side of things. And I think the X side of things is fixed purely from the ray tracer's perspective. I think that the way we're calculating which screen tile to look at, and then in turn, which screen tile to look at, and then in turn, which Froxels to then check for spheres, we end up being off by one and going down the other side and then not hitting anything, right? So I think that's the way, that's what's going on there, basically. Right, I just need to quickly go and get another drink, and then we'll fix this Y issue, and I think the X issue should just be, yeah, should be pretty simple. So yeah, I'll be back in 2 minutes. BRB. Right, welcome back everybody. So, let's try and figure out why the screen tile that we're picking to put this sphere into is off on the Y on an even number of, when it's got an even number of grid cells along an axis, it's off when you get near the edge of it. So it's kind of why is it off? Right, so we can just apply it to the visualization code and then fix it later. So where it's working the min and max, in this case the min y, or the max y actually. Right. It would be the same for the x-axis as well, to be honest. They're both the same. Right. So we run over this again. So you get your left and right bounding box positions, right? You get your min, we bring it, where is it? Yes, we get the depth of the screen tiles, right? The Froxel dims, the X and Y of those in, so we bring it from screen space up into the depth here, right? Round our left and right down and up respectively, right? So you get your left and your right. Okay, yep, that's fine. So we might as well, to make this less wide, just do it all in here. Okay, so that should, left, right, okay. So then we can just simply remove this here, and it should make it as wide, a little bit more readable. Okay, so you've got those like rounded yeah, so we divided it by the dims at that depth. So this would be so this is 0 here in the middle. That line there is 0. This line here is 1, 2, right? So this would be on the 1. So we divided it by these dims here. Is that correct? Yeah, so you're saying, you know, from here, how many? So that's be 1, because the dims. That's the problem, isn't it? Yeah, that's where the whole problem is existing from. And that's the reason why the further you get to the edge of the camera, okay, we've got to do a different strategy. The further you get to the edge of the screen, the more... Okay. Now, is that right? No, because it's at this depth. The cells will all be the same size along that x-axis, for instance. Yeah, that's fine. They'll all be the same size at that depth. It's just not drawn to scale. That's the problem. Right. So yeah, we don't. This would give us like 1, for instance, on there, and this will give us 2, right? On the right. So you'll floor the left, and then you basically want to say, right, so you've got 4 of these guys, divide that by 2, add 0.1, round that up. So this will essentially just be, also round it, not round up. This would then be, so 2 plus 2, 4. Rounded, yeah. Wait, is this? That's wrong. Oh no, sorry. 1 plus 2, right? 3. So it rounds you to 3. Climb between 0 and 4. That's fine. And the max would be 2 plus 2 rounded up. Yeah, sorry, because this might not be, because it'll be here, wouldn't it? It'll be, yeah, it'll be, yeah, so with that number sealed, wait, divided by how many of these? And then you round, so it'd be like 1.65 or whatever, land here. You round that up and it'll be 2. Excellent. 2 plus 2, because that's 4 over 2. And that'll get you on, obviously, 4. So your range along the x-axis is, between... Wait, sorry. And then to complete that, we basically... Oh, yeah. So your range is basically from cell 3 to 4 exclusively. So you just obviously be going in 3 there. See, that feels okay to me. That was an example on the x-axis, and then we're coloring it. No, something's still a little bit off. We're moving a bit too fast with the controls. If I were to slow it down, maybe we could start seeing something else. The speed, let's drop that by 10 times. Also trying to write my language in Rust. The crane left code gen stuff has got very good. Cool. In Rust, eh? It goes a bit early. The further you go up, the earlier it's like, oh, I'm on the next one. Oh, I'm on the next one, right? So the further you go up, the more, or the earlier it is to jump to the next one. Which would mean what? See, I still feel like it's some. It feels like it's something to do with the projection, though. You know. Like, this bottom bit that's been clipped off is the back side. And the front is there, but then you're only doing... Yeah, is it because we're doing it at the front? It can't be, though. We're seeing the size of a Froxel at that depth. Yeah, oh, no. It could be that we're doing it from the front. It could actually be we're doing it from the front. The size of a Froxel at the depth. It is because we're doing it from the front, damn it. Right, let me draw it again. Let me draw this version. Here, you'll be like, oh. So you'll be like, this is the width of a Froxel, right? Which is fine. But you'll go from the left point at the front and you'll round it down to this bit here. But really, this one is actually up here and it'll round down to this one, meaning it affects these two cells, right? So that is the issue. We actually want... Do we want the furthest back or the furthest... So what do you want to do in that regard? So you draw your box. When you draw your bounding box, I think you want to take the min of the... Yeah, it's one of those things where the left and right will need to get... No, you always want to take the back, is that right? At depth. It might be at far. So let's get far as well. We'll probably need far. So where's near used for the one that you bin it in? Yes, that's why you'll get cut-offs. Right, but then do you always want to use far? Because you kind of want to look at near and far and get the min from that, really. Yeah, entirely depends on your sort of what edge of the screen, if you're in the top left, bottom right, that sort of thing. So if you're in the top right hand side, your furthest left is going to be the bottom left hand side, right? So sort of the opposite. So what you really want to do is select the near and far based on that. And your furthest right would be the top, would be the near right. Okay. So when you're doing this sort of near and far thing, so you're kind of getting the... And then we'll just do depth 1, depth 2. We'll just call them depth 1 and 2, or 0 and 1, whatever you want to call them. So these guys need to basically be like, well, if I am more to the right, then yes, if I'm more to the right, my left needs to be the far, whereas on more to the right, my left my near needs to be the left, something like that. So you're saying if sphere dot your view space one. Yeah, so that is negative, then you want to be using the near depth. Whereas if it's right, depth x, depth y, is that right? No. Yeah, x 0, x1, so that's just the other version of it. The other way around. Then you just do the same for the y. Okay. So these numbers you use when you do your division. So that's your left one. That's your right one. And you want your... I really dread implementing generic, so I have no idea where to even start. Yeah. Well... Yeah. Generics are... You basically need to generate another type. Right? Or another version of that same thing. But you then... Like... Then you're sort of finishing it up, right? So essentially you have a bunch of... you have a version of it which has one or two fields which might have like a t, you know, like a compile time argument in there, and essentially when you end up using an instance of that type which has been fully template, you know, with the template properties all sorted out, you essentially make a new type, but you'd only make a new type in the type system if the type hasn't already been made in the past, right? So you're just essentially making another instance of that type, but you finish it off and replace that sort of t variable with the actual thing, like an integer, right? So yeah, it just takes, you basically need to have sort of an abstract type that then gets made into more of a concrete type, right? Same with functions, right? You have an abstract function which has most of the implementation in there, but it can have some compile time aspects of it that need to get fully, which need to get made concrete later on, right? That's basically it at its core, right? Okay, I think that's the answer. Alright, that didn't work. Hey Solly, how's it going? Why is it not going anymore? That is not good. Not good. Oh, I need to multiply these dims by it. My phone's saying reconnecting to chat, but I think it's still running. Okay, still running here. My chat's frozen on my phone. Oh, this problem. Not a fan of this problem. What? So what was it doing before? L.x.y. So it's .x .y .y. Let's try that. What have I done? Did I compile? Okay, so it used to be oh, I didn't do a multiply, I just did a comma operator like an absolute melon. Right. Absolute melon. Right. That'll be the fix. Come on. Look at it go. No. Oh yeah, it's fine, that's fine. It's going a bit early. No, it has to go a bit early because because the bounding box. I think. It's weird though. But yeah, it is going to cut. That's fine. It's cutting. It's fine. It's just we're just seeing the way these tiles are getting allocated with the thing in it. I would feel like, right? Maybe that. Yeah, it's the bounding box. It's going to be off by a bit. Yeah, it's going to be off by a bit. That's fine. That's fine. Right. So we've solved that problem. Which we can move that over. I just want to fix the other issue now. And I think along the x-axis, as you can tell, is really really off, really bad, right? And that's because it's got an odd number of cells along the x-axis. And I think that problem is to do with the way we're ray tracing. When we ray trace, we figure out what pixel we're at, and then we go, oh, what screen tile are we in? And then we go down and check the tiles, the spheres, or the Froxels for that tile, for those that pixel, right? And we test against the ones that we come across. Now, the thing is, I think that is off because if it's an odd number, it's sort of like top left origin. So it kind of goes a bit like, it's weird. Top left origin. So the middle is like, the middle is like, it won't be the full one. This will be cut off on the screen because it's had to round up, and the middle will be somewhere like here-ish or whatever. It's really odd, right? So what we decided to do in this for this problem is we decided to make it, if it's an odd number along the x or the y-axis, we actually make we make the tiles be center aligned down the middle, always directly down the middle, right? And if it's an even number, it's just split down the in between two cells. So this would then mean that the way we pick this tile has to account for that difference, basically. So when we ray trace up here, this tile index needs to be calculated accordingly. So basically there's this bit of maths here that we use. So let's plop this in a little thing like this. We can put comments around it and make sense of it. We could probably make this better as well, but I'll put a comment and describe it and we can come back and fix it later. So let's just do that. Seems legit. Delete those two. Then we need to replace tile index. Okay. So run this now, it should fix it. We can move on to something else. Right. It's fixed something. No, it hasn't. It's definitely changed something. Right, so the way that things are being allocated is wrong. On the Y, it's completely fine. But the way that X is being allocated, all right. So let's look at this debug. It's drawing the background tiles. Right, Froxel dims near clip space. Why did we times it by the aspect ratio? That escapes me. Right, let's change the Y by that. It's okay if the Y clips. I'm just seeing it allocates them. I don't think it's to do with that. Right, so near clip space, we shouldn't have to times by the aspect ratio, I'm pretty sure. Let's just think about that for a moment. Because it's the same width and height, these Froxel dims. The width and height, no matter the aspect ratio. So, okay, so this is working out the left. We should really improve these names, not gonna lie. Left, right, bottom, top. Okay, so why would the width be wrong? Like, the way it's allocating the... Like, it's just not doing 2 at all. Which feels off. So where's the number that we can modify to make it bigger? The earliest number that we can modify. So obviously these min and max x's if you... Yeah, I guess it's this guy up here, innit? So we change... This is like 48 in this example. Which we should maybe make it 16 when we're done. Maybe not, maybe it'll be too many. Anyway, we'll see there. So, you got Froxel XY. Yeah, x what's green space times. Okay, so if we simply make this... Yeah, but this is not the number you want to change. Depth left. Seems legit to me. Um... So why is the Y different? All seems pretty fine. Right. um... Let's make that better. Right, let's just reuse the same code basically. Right, so it's less than or equal to that tile index. Some offset applied. Let's make it reuse the same code. It used to be called tile chord. Let's bring that back. Damn it. That one. Okay, so... So tile chord would just be this. It's the y-axis in it. X, X. Okay, dot y times plus X. Just flattens it out, right? Pretty standard stuff. So with this tile coordinate, should be able to do is just reuse that. So it's the same stuff at least. Still not going to be the fix, but at least we're not duplicating code. Okay, so we've still got the problem. The Y seems to make sense where it goes to about 2 or 3 of them, whereas the X doesn't. It goes 1 to 2 of them for some reason. Why? We're not using the aspect ratio anymore. We should be fine. Okay, so the Froxel dims near clip space. Okay, so this can just be simplified actually to depth 0, depth 1. No, because it's 4 corners. True. Yeah, this can just be simplified to XY size new clip. It's just the same. So that would just be this. That. What else? So the left and the bottom need to be the same. On the nears, yep. On the fars, yes. Um. Hmm. So it works fine for the Y, but why? But why? Let's make them both even numbers of grid cells along the X and Y, and that will help us find out. Let's put it back to 16 for a tile size. So, right, they're both even numbers, and it seems to be fine the allocation. We're accepting the clipping to still be, because we haven't fixed we haven't copied the code. What we're talking about is how the cells that it's being, put into, and obviously 16 by 16 might be a bit small. You might be better off increasing this number in the future, but it might be perfectly fine. I'm not sure. But yeah, it's binning it in all of those that we're seeing here, right? That looks good. I guess it's just the odd number. Right, when it's the odd number is the problem. Yeah. I'm even putting it off into the distance. And that's just, it's looking fine the way the ball is allocating the new slots for, where it just goes, where it gets binned into, right? So that's fine. So when it's an even number, absolutely fine. So when it's an odd number of cells along an axis, that's when it's a problem. So then it's to do with this logic here. We know that. There's this rounding logic that it's doing. That's the problem. Okay. So we removed this. What would it... Alright, what have we done to make this better? Well, I'll probably have to explain the problem again. So the issue is, if you have an odd number of cells along an axis, the middle is directly, like the 0 like 0 origin is here, right? So when you're sort of working out the min x and min y, so this is numbered 0, 1, 2, 3, 4. Like we want to work out in this space, basically, what is the range of cells that you hit. So this guy will be in between 2 and 3, right? That's the problem. You want to bin it in 2 and 3. Okay, that's the problem that we're dealing with. So the problem is you've got your thing like left, which would have been this guy rounded down to the nearest one, so that actually put it on 0, right? Then it would have done 2.5, right? Add 2.5 to it. That'd have been, yeah, obviously it's 2.5. Then you'd add this 0.1 to it, which could have been 0.01 or whatever. It doesn't really matter. We just rounded it and ended up rounding it up. So it rounded up to 3. And that would have been fine, right? Because 0, 1. Aha. That's not it. You actually want it to round down for the min. And then round up for the max. So maybe I got those the wrong way around. Okay, that might have been it. Alright, this looks good. I don't know if there's an over allocation though. So we're gonna keep these negatives, and if that is fine, then it's a bit of a question, right? Okay, that clip's wrong, but when it goes left, perfectly fine. Got it. So, actually, is it perfectly fine? Let's check to see if we're not over binning it. Right. So we keep going, and then there it's like, see, it does it sort of on the halfway mark. That feels like it's doing a bit too much, right? Whereas on the Y, it does it when it kind of gets near the edge. So there's something wrong with the rounding. It's over binning it. So how can we fix that? So it's something to do with the whole. So we should probably be adding 0. We should probably be taking away 0.5 here and then adding. But that's not really going to do anything. I don't know though. We'll see. Right, still the same problem. It's just made it worse for the Y. So kind of an epsilon was fine there. But let's just rerun through the thing. So you've got this. This would be in. If you ran down to 0, fall down to 0, you'd have added 2.5. It would actually just be on 0.5 now. So you would be kind of. Sorry. You added 2.5. Take away from 2.5 just a little bit and then round it. So just land on 2. And that's the box you want to be in. But if you had something like this, with your box around it, your left would have been rounded down to this other one, right? Which is not right. So if it's like so maybe you want it to round down and then just increment it by 1 or something, just so you handle it better. Yeah, so if we did it, that's the reason why we probably did it this way. No? That'd been on 2.5, you'd have taken it down to 2. Yeah, but it's only when it's an odd number. That's the annoying thing about it. So we could probably do that offset thing again that we had at the top. We had this sort of offset thing which is really horribly calculated. But that's the number of screen pixels or something. Offset by to center it on the screen. What do we need to solve? Yeah, we just need to say if we are an odd number along that axis, odd number of grid cells along that axis, the way we need to, so before we clamp it, we might need to like add one to it or something. Right, so the line would be, so imagine if it's Froxel grid dims X. So over 2, so it'll just be, right, so say if our 0 origin, where would that be? If you notice down the middle of the screen, isn't it? Yeah, so it's going down the middle of the screen. That's very terrible. Much better. So it's down the middle of the screen, and you know, if you have something like this, that's going to be rounded instead of to the nearest one of these guys, it's going to be rounded to the nearest one, rounded down to the nearest one of them, like halfway through, because it's an odd number. So if it's an odd number, before you do the round down, you kind of want to add a 0.5 offset to it. And then the round down and round up will be completely fine. And that's what we're kind of missing, right? What we want to say is, and this will be fine because it'll be the same across all threads, I guess, right? Oh no, it will be. There's no problem about that. So you just do something like this. Or if it's an odd number, you take your left and you add 0.5 and your right, they just did to all of them, right? Bottom, and top, right? And then when you go into here, sorry, that's just the X. We need to really just delete those there and do the same for the Y. We need to then not care about, yeah, we care about that, but we don't care about this bias. Do we care about the bias? No, I think that all stays the same. Let's just run that. Well, that failed. Because that should have been a takeaway, that should be a plus. I think I undid it a bit too far. Okay, that appears to be working better along when you go that way. When you go this way, are we over allocating the max? Like, it's just going, it's one too many. So I think on the max side of things, do we not care about that? Is it really just on the mins. Whoa. Something's off. I think it then means we need to do a takeaway here to get it. Maybe we just need to floor it. Wait, it's getting floored anyway. Oh, the value's getting floored. So this post-rounding thing might not matter anymore. Let's give that a go. Yep. Alright, it's looking good. So now we've just got to bring those changes back to the actual code that does the binning, because this is just in the ray tracer and we're just debug visualizing where it would actually get binned, but we haven't updated it yet. And that should fix all these issues there. And then we just need to drop some comments in by the code so we can sort of make sense of it when we come back to it, right? So we're going to take all of this and I don't know what we'll do. We'll just take that and we'll adjust. So it's like calculate counts. Okay. So we'll just dump it in here and we'll just adjust accordingly. So essentially we want to keep this guy. It's there now. All of this wants, this wants to get kept. This will get deleted. So there's that. We've added a bit more code. When we did some performance optimizations, we could probably clean this up a bit. But for now, we just wanted to get it to work, you know. And then we'll copy this again. And again, we've basically got one which pre-allocates. It just counts how many spheres get binned. Then we allocate from those the counts for each Froxel, and then we actually do the same thing and do the binning. Again, we would probably want to fix, make that a lot more simple when we optimize it. So I don't have to duplicate code and whatever, but for now it just needs to work. All right, so now we shouldn't see any problems. I'm moving it closer to the screen. It's now increasing the amount of bins. Oh, that's a bit of a problem. Damn it. Okay. Close though. Very close. Okay, I think I know what the problem is. It's that center position thing. I think it should be quite an easy fix. Yeah, so around the center position, see it sort of flips there? The other side with the allocation or the binning. It's because we're tying it off from that sort of center position V space when we do this sort of check here. What we really want to do is say if the left itself is less than, then use the near. Rather than the center position of the object, something like that. Yeah, so I think we want to just do something like this. Just do it twice. This will just go down to something like this. And you just do something like that. And then this one would just be... And then in here you would just go, oh yeah, if the left is less than, oh, if the right is I think you still just use the left here. Bottom. Wait. No, we should be using the right. I did the right with grey then, just do it that way. Bottom and top. Okay, that should be the fix. Just got to copy it into the other places and give that a go. Yeah, this is the debug code, debug visualizer, which we'll probably delete in a second. Oh, we might keep it around. I'll have to retype it otherwise. So we've done the optimization. Right, so bring it closer. We'll see. Oh, it still buggers up. But when we go across these bounds, it smoothly goes now, right? So that's definitely better. This smoothly goes, but it feels a bit off. Oh, it's a bit... something's wrong with that right version. Got a bit of a typo somewhere. Is all. Where is the typo? So the right appears to be off. Ah, does need to be less than. Whoops. Huh. Right, let's fix that. And voila. I think we've got the perfect binning now for these Froxels. Yeah, it's looking good. It's obviously a bit too big here, but that's because the access line bounding box around this guy is going to be really just the way the bounding box ends up being around it, I think. Something like that. But we're not going to have this problem. The problem we're going to have is probably something like this, or even smaller. So it doesn't really matter. Right, so this is going to be precise enough. Oh boy, what is that? We're seeing the tile allocation just fine. But it's not rendering. Did we miss one of them? What's different with the code then in... Right, first of all, let's get rid of this aspect ratio stuff. I don't know if that's having a play in it. But anything with aspect ratio, we just can get rid of that. That wasn't needed, so it's not going to really bugger anything up. So the interesting thing is when we run it, it looks fine. Right. Okay, it's definitely an odd number thing, because the y-axis is fine. It's something to do with those odd numbers again. But it appears fine when we have the visualizer, but the actual binning code is messed up somehow. This is the binning code. This is the visualizer code. So why would this work? So something to do with those odd numbers. Odd number of cells along the X and Y. I thought we sussed that with this thing, right? And this thing down here. But if we go to the other code, it's the same for those pieces of code. What? There's Froxel Z, that won't be anything to do with it. It's to do with the X and Y. What is this issue? See, when you're at this depth, it's fine. But as you go further out, it starts to have problems. It could be the way the binning code is iterating over the, like, using this information, right? So it starts off at min, goes all the way to max. That's completely fine. Maybe it's the way we're assigning it to these things. Yeah, I wonder what Z we reach. Should it do a GP print? See what we get. See what number we get from the GPU. GPU says 6. Right, when it hits 7, it starts to have problems. I think 7 is the bounds. Yeah, there's something really odd with the way we've done. Like our Z is in log2 space, which I think I want to change that later on when we optimize it. It might be fine. But yeah, so when we get to the last one, it's like, you know, it has a problem with it. Oh. It's flooring it. I think it's log2 plus 1 floored, because this far is 128. I'll get you 7. So you're 0 to 1. Yes, you have 0 to 1. And obviously 1 to 2, 2 to 4, right? Yeah, so maybe no, it's fine. 7. Yeah, no, it's fine. It's fine the way it is there. But when you get onto 7, it's got a bit of a problem. Why? See, it's in this plus Z. Ah. Right. So if this is log2 near depth, and it ends up being on 7. Right, it needs to be take 1 then. Because if you're on 0, wait a minute. If you're between 0 and 1, you're gonna get. See, it'd be good to know what depth we're at as well. Can we see the depth? And that would make a little bit more sense. Right, so the depth at the moment is... Right, here it is. Okay. Ah. So it's actually fine. When we reach 128, it's like... which makes sense because it goes out of bounds. Especially when it does this add, it actually reaches out of bounds. Wait a minute. I'm 07. No, it doesn't go up. Yeah, it ends up being on a different one. See our artifacts. So it should be. Yes, it stays in bounds. It just ends in another. It adds it to another screen tile that it shouldn't be in. So we actually go out of bounds there. We just bin it into something else. Yeah. Yeah, we should probably not bin it at all, basically. Right, let's increase our depth, at least. Let's go into the shed, and let's up it to like 512, I don't know, maybe 1024, all the buckets. So I think we have 10 buckets, right, on the depth. So I guess it's kind of cool for stuff that's really far away. But yeah, so this will now allow us to go past 128. Then delete the code. But yeah, so this would be fine. We should probably deal with that issue though at some point, obviously. But yeah, it's looking good, right? Cool, so let's just bring the number back down to 16. Where is it? 48. Bring it back down to 16. 16 is probably a little bit... You know what, let's bring it to 32. I do feel like 16 is going to be way too small. Especially when it's got layers of tiles, right? Layers of screen tiles. Maybe even 64 is a good size, to be fair. Because you'll be binning it in way too many places, right? If it's big. And you've got layers. So it kind of... but the layers do get bigger. Wait, sorry. The layers... Yeah. No, it's fine. But yeah, we've got like edge cases to handle definitely in the future. But I think that's the Froxel stuff done. I just want to turn off all the debugging stuff basically. Froxel Raytracing. We should probably drop some comments in so we don't forget about this stuff. Yeah, so this one just debug renders all of the tiles. That's not as good as I hoped because this needs to be multiplied. By a smaller number just because the number of tiles we've got. Oh. Maybe a bigger number. What's wrong with my tile index now? Why is it? Right, let's look at that for a sec. So these two are red. What? So we go back to that. Are those two red? Dun dun dun. So it's done the 64 by 64. Right, which is 4096. So if you enable that one. Maybe it does need to be smaller. No. Yeah, I think it's just the way we're using that tile index or whatever, but it's fine. Or maybe we did like a prime number. I'm not sure where's the nearest prime. Prime's in 1000. Let's do, I don't know, 997. I might. No. It's because it's the way the X and Y end up being. No, I'm confused. It's alright, it's just a debugging thing, we can fix it later. Yeah, it does look, I think it looks kind of wrong with the way that the debugging thing was, but it's kind of fun, it's just debug stuff. So let's bring back the full model, and let's see if it's, you know, if it's, if it all works. So we've got an if one knocking about, I think. Yeah, here we go. So this just basically clamped it to 1. But now we're going to bring back the full dumbbell ship. And here we go. So let's up the speed. So if we don't see any clipping, then got ourselves a win. And then we can move on to something else. Here's our ship, goes off into the distance, no clipping, Froxel binning. We've seen some jumping pixels, but that's just the ray tracer, I think. With the aliasing. There's some anti-aliasing, basically, they sort of a little bit odd. Yeah, we need to fix that, but no biggie. So what we can do now is we can, you know, we've got 3 different renderers, right? We've got Froxel based acceleration structure, we've got screen space, tiles. What else have we got? We've got a BVH. So we can actually render those 3 all at the same time, and we can just check on how they do. So for now, we'll just do it, right? Gotta find it. We'll just enable all 3 of them and just compare them briefly, but it's not going to be anything we take home with and be like, oh, this thing is just better, because we've still got to optimize all 3 of them, and we want to optimize it for a bigger scene. So what we want to spend time on is actually making all 3 of them work for a bigger scene, and having models, instances, more complex models, and just filling it up and just seeing how much we can push for all of them. So this is all 3 of them rendering at the same time on top of each other, and these are basically the results. So the BVH one is about 0.056, the Froxel one is about 0.28, and the tiled one is about 0.13. Now I would expect that the Froxel one to get better when there's tons of stuff on, like a whole scene, and again we've got to optimize it. But the binning is definitely quicker, I think, for the Froxel one. yeah, the binning is quicker for the Froxel one. So it bins quicker, allocates a bit slower, which we could probably fix. Yeah, we could probably fix that. And it just ray traces slower at the moment. But it depends what it's like with a full scene with tons of balls, because I think the Froxel binning, it's got an advantage where we can basically early out. That's pretty damn cool indeed. Thank you, thank you. Appreciate it. The real question is, what do you not have? Well, I don't have models and model instances and a camera system. That's what I want to work on next, Ray March, is actually having a camera that just moves around the scene. Yeah, that's something that we want. And then we can have models and model instances, and then we can basically test all these acceleration structures and be pretty sweet. You know what I mean? Yeah, cameras overrated. Who needs a camera in a game? Yeah, you know, maybe we won't need a camera. But anyway, we'll make a camera. So the biggest advantage of the Froxel system over the screen space one is this. You'll have these bins, right? Okay. And you basically go through each of these bins and you check to see if there's anything in there. And when there is, you test your ray against it, right? For the ray for the screen pixel, right? And if you hit that thing and it's not transparent, wait, if you've hit that thing and it's not transparent and you've got nothing else left to check inside this Froxel, you don't have to check any of the future Froxels at all, even if they've all got tons of spheres in. So this is the main benefit of this Froxel-based acceleration structure over the screen space one, which will have a lot. I think there's other optimizations where we can basically reduce the amount that we bin into this Froxel space. Say we have a massive 3D model. If it's a static model with not a lot of if it's a static model, it's got a whole bunch of balls, right? And the balls don't move that much. We can probably assume, right, if the camera's looking at it from this angle, right, we could probably assume that we only need to bin the outer side, and we could probably just not bin any of this at the back, right? So there's definitely some tricks we can do with a view space acceleration structure versus the BVH tree. The BVH tree is really great for doing basically lighting, where we need the whole scene in this BVH. But in terms of like view specific optimizations, we can really go fully into those, which would be pretty cool. And you'll just get a much better optimization. Pretty sweet. Yeah. So, I want to check this boy in. So after the stream, for those who have access to the code and stuff, you'll be able to get it and have a play and stuff like that. So I want to do a git commit add Froxel based binning for sphere ray tracer. Right, so we've got 3 acceleration structures, and there we go. So the next thing I want to do today is I want to look at, I need a matrix, right? You know, we just need to build a 4x3 matrix basically. Like in HCC we have this, which is my C2SPIV compiler. We do have a bunch of matrices already, but you know, I think this needs to change, because we've got a bunch of like 2x2s, 3x3s, and 4x4s and all that. I think we've only done square matrices here. I could just use this, to be honest. Maybe I'll just use one of these. I could just use the 4x4. And I know this one works. So really, we'll be better off with a 4x3 with an implicit 4 row, you know. This, I don't have any identity functions either, right? Yeah, there's a whole bunch of stuff we don't have. So, you know, yeah, I might keep these around, but they're not really going to be that useful. Yeah, so I think I want to make more specialized matrices, just sort of like 3D transforms. So just storing less floats, basically. Fun type checking. What do you mean by type checking? So we want to go into the core, and I want to like just essentially add. I've already done it in shared before. We've got this UI matrix. Oh, it's in the UI shared. It's like a 2D. We've done a 2D matrix, which is like a 3x2 matrix. So essentially, what I want to build is a transform 3, basically. So we share between CPU and GPU. So it's just a 3D transform. Maybe call it 3D. So the idea is it's just going to be like, you know, I want it to be, I think it's column major, so we can just get access to the axes, right? I think that's the way it works. I just spelt Ray instead of row. So I think, yeah, so row major you go in this order, but the way you store your things is it's so if it's a 2x3, or is it 3x3? B, you store your translation at the bottom, isn't it? Because it's a 3x2. Yeah, sorry, it's a 3x2, isn't it? Because it's I think so. Yeah, this. Right, here we go. So this is a 4x4 matrix. So we want to. This is not really great. Yeah. So this is like. These things make it really confusing. I've just got to understand how you interpret it. So, in terms of the memory, I remember struggling with that last time. I tried to make a language. Oh, type checking. Yeah, I don't know. It's not that bad, right? You just have a syntax tree, and you just recursively descend down the syntax tree, and check some types, and then basically infer some types, and then bubble the types back up the tree, do some checking, you know. Yeah, I think it's just one of those things where you just got to sit down and think it through for yourself to get sort of grok it, basically, isn't it? It's only because I've done it in the past that it's now easy for me. But yeah, I can imagine. But yeah, just make sure you think it through before you write thousands of lines of code, right? And have a bit of an understanding of like the tree you're going to generate, and then how are you going to type check it and stuff like that, and just think it through, you know. Yeah, so what this just feels very confusing because they've kept the one. Right, so column major. They've just changed the way they highlight it. Um, yeah, so where's the x axis? Yes, the x axis, so x. Right. That just is. Should I go to the website and see if it clears any of it up? I need to figure out which one I want, and then we'll just go into that. Um, demonstrates packing into row major. It's called row major because all three of the rotation basis vectors, as well as the translation vector, are stored in rows of the matrix. No, this just doesn't feel right. Basically, one of them is x, 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 y, 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 z, 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 z. And the other one is x, y, z, x, y, z, x, y, z, right? Or w, x, y, z, w. So it's basically SOA, AOS, right? But I just need to figure out which one it is. Always forget. I think it's the column major gets you your XYZ, XYZ, W, that one. Right. This is our boy. So, yeah, column major is your XYZ, XYZ, right? But we'll go in and see if there's any more information about this. Really? Damn you, Medium. Create an account. It's a little too much. All right, now I just got to scroll the article. Dun 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 dun. Right, so where's that? What is it called again? Over scroll or something like that? Oh, my web dev days. Overflow, something like that. I forgot what it's called. Overflow. Auto. Right. Okay, they've actually deleted the thing. Maybe we can't read it. It was not meant to be. Hey there, Rosmusco. How's it going? Going good, thank you. We've just finished sorting out the Froxel-based binning. So we're binning Froxels. Pretty great. I'm just trying to figure out which way round the column major versus row major is and to be for certain for it. Yeah, I think I want column major because it's basically structure of arrays. Wait, is that right? No, it's array of script. Yeah, basically I want the X, Y, Z, W all next to each other in memory. I'm trying to figure out which way around it is. Maybe the images isn't a good way to look at it. Yeah, it's all well and good. No, yeah, this order. I know that for sure, but it's just which. I think the way they define it is it goes downwards, right? is each column is stored after each other. Yeah, I get that part. Then the row major is each column stored after each other. I get that bit. But when you have your sort of transform matrix, right? The basis vectors are stored in the columns. Is that right? Is that right? They're stored in the columns. So you have your sort of yeah, they're stored in the columns. Okay, perfect. There we go. We got it. So here's column major. Column major. Thank you, sir. So this means we can just get access to the axis vectors and stuff like that. So we'll just be doing like float. So what we're doing again? Yeah. So you want to get your columns. Or you could just get the axis vectors like so. So we could basically union it. No, I can't union it because there's a I'm using it on the GPU. But yeah, we can get the axis vectors and then we can get the translation part. So it's 3 axes plus another one, which gets you 12. There you go. And a vector on the right. Yes. Yep. Thank you. But yeah, so I think we will just be defining stuff like this, where we'll just be like, essentially, I think I'll just put it all in line. So we'll just be like, yeah, we'll make it all in line, that way the compiler can just do what it wants. And plus, it'll work better on the GPU that way. Hey there, Sleeping Mushroom, how are we doing? So then we'll have like an identity. So T3D, I don't know, identity T3D, I think I'll call it. Should probably, anyway, that'll just get you the identity. That could probably just be, that could probably just be a constant. That'll just be, yeah, I had a realization about how the matrix multiply works today. I was thinking, you know, because I knew how you could basically translate a point into another space using the axis vectors, right? I knew that. Then I was thinking, hang on a minute. The whole like way the matrix multiply works is basically that, just multiplied across all the axis vectors, I think. I think that's the realization I came across today. But yeah. Because you're transforming, the way that I think about it at least is you know, you've got one matrix like that and you've got another matrix like this, and you're essentially, it would be better if that, anyway, you're essentially like, when you're like, it'd be better if I had two that were kind of different, but anyway. I guess this would just be like unit length vectors, right? When you're sort of saying, how does this vector here go into this space? And it will actually just be an exact match since they're unit vectors, but it was a little bit more, it will sort of just go around a little bit more like that. This is just with rotation, though with scale it will obviously be a lot more. But yeah, you're essentially taking these vectors and sort of moving it into that space, basically, isn't it? Something like that. So it's as if like you've got like a point and you're moving it into another. So it'd be something like there. Essentially, you're taking this sort of like that vector and you're translating it into another space. It's like that, but for the axis vectors of one matrix to another, I think. That's my sort of thinking. The from notation, yeah, world from local, definitely. Yeah, we use that at work. It's really good. It's a really good notation. Yeah, for those who don't know, you can basically have your matrices like world from local, and you have another one where it's like view from world. And basically to produce view from local is simply like basically you just line the buggers up, right? So you line up the end of that with the start of that one, and then it basically cancels those out and it produces your view from local. And you do the same for the multiply and a vector as well. You have your sort of vector in world space, right? And then it just lines up. So rather than have it in the type system, you have it in the naming system, and it's just way better. Because then there's no templates everywhere. Pretty sweet. I like it. Oh, that's what I do at work. This one. 0, 0. Oh, sorry. 1, 0, 0. Column major all the way. It's kind of funny as well. Like, if you have one matrix in column major and another matrix in row major, you can basically multiply quicker because it's already transposed, and you just do it. You know, your multipliers will be linear in memory or whatever. No, sorry. Yeah, you'll be able to use SIMD on it, and you don't have to transpose your matrix basically while you're doing the multiply. I think I've heard in the past. I think I heard that people have done that in the past. It's really weird though. Translate. 0, 0, 0. Right. So, oh yeah, column major, 4x4 matrix, 4 row. Wait. 3x4 matrix because it's 3 rows, 4 columns. Matrix with an implicit row. With an implicit row 0, 0, 0, 1. Right, something like that. Because that's why we haven't got a 1 on the translation, because it's actually off the end of it, right? Is that right? Yeah, that's why we haven't got an extra 0 here, because they're off the end of it, right? So jobs again. So what we want to have is we want to basically have a so I can't have pointers on the GPU. So if we inline everything, because it's gonna get inlined anyway, on the GPU. Yeah, CPU. Well, yeah. Anyway, if there's problems there, we'll fix it. But for now, I just need to make it work on the GPU better. No. Oh yeah. Yeah, the problem is I don't have pointers. That's the issue. I was thinking header and source file, but yeah, no. We can't have pointers on the GPU. So we're just gonna have to do it this way. Just inline it all. So what functions do we need, right? We want to sort of multiply T3D. So this is going to multiply a transform guess I could just do that. Okay, so you've got a and a B, 1. Right, this should be pretty... Well, yeah, we've got to sort that one out. We can do it though. Let's just roll the ones we want. So we want to then multiply a... we basically want to multiply we have one where it's multiply a point, and the other one is multiply a... one is multiply a point, one's multiply a vector, right? And then we probably want to have one which does it with a... where it's a value instead. So we have multiply v... and then multiply p. Yeah, you know, I'll just have them separate like that. I need my maths library included here. Right. I was thinking about having another one where we can make it a vector 4 and just have that last coordinate be 0, 1 programmatically. I'm not sure how useful that is going to be, so I guess until we need it, I'm just not going to do it, right? Okay, so we also need so we need those type of guys. We also need a way of actually making one of these things, right? So we need identity, probably translation. See, there's a way that we can get it to do all of them as well in one go. But yeah, so we're just taking a translation. We also want identity rotation and scale. So yeah, what do you want to do for... Yeah, this is where we should probably have a quaternion for rotation, right? Oh, I'm not sure though. Right, let's just roll with that for now. But yeah, then we might want one which just constructs it all from the raw stuff. There's a program that we can use that basically generates this function for us. Because I did it for the 2D one and it was pretty handy. And it'll just be better than doing it by hand, basically. Yeah, why did I copy all of that? Just do that. Right. So I think those are the functions we basically need to end up doing the camera. The camera system. And if we need any more, we can just add them, right? Yeah. Okay, I'll just be right back. I'm just gonna get some more, another drink. But yeah, when we get back, we'll just go ham at this and see how far we get, basically. Right, BRB. Right, welcome back everybody. So I'm pretty decent at doing this matrix multiply, I think. But right, so translation, this one's dead easy, right? Basically, right, we just want to make this. Yeah, so I think the one I'll have problems with the most is probably this guy. Identity, where it does all of them. I'll probably have problems with that one. We need to get some code generator out. But the rest, I think I should be quite okay with. So let's just roll it out. So I think we can just do, let's call this T, great name. Then we'll just do, yeah, why does it have to be a function? We'll make it a function, screw it. Something like that. And then we'll just say translation. And then you just return T, right? Ta-da! Not rocket science. Now for the rotation, this is where I need to. I might need to have a bit of a think about this one. So, because they go into, for 2D, they go into there. Right, for 3D, I think they do all of them, right? Because you need to fix all axis vectors. But I think it's only in a very specific spot. Right, here it is. I know it goes in all of them. Right. I'm not really sure about that one, to be honest. Okay. Yes, there's this program that I got made aware of by Cranston, I think it was. And so I'll bring it open in the matrix.py. This is it. So basically, he gave me this file, and it had all this like this Python file. And it's called simpy, and he basically like effectively it uses like reflection or whatever when you do your maths operations. You can make matrices, and probably more things. Do these sort of operations and then call simplify on it. And okay, let's explain this better. So effectively, you can do these matrices, right? Do these multipliers, and you can just print out. You can print out the operations. And notice how we're using. So effectively, it tells you how to sort of. What can it do? Yeah, it can basically simplify maths expressions for you and then generate the code for it, basically. So it can take in like different variable names, right, that you can label, and you can basically do these multiplies and it will remember everything that you've said and basically just produce the code for you, which is pretty sweet. So it's actually a really good tool when we did that. Wait, so this one we'll probably want to use when we do that final one, where we supply all of them in and we want to just simplify some code. But for this rotation though, I probably just need to use another resource because it seems like, yeah, it's not going to work that way. Is it, 4x4 or 3x3. That's what I mean. No, it will be a 4x4 then. Um, right, any combination of right, the rotation matrix. Here we go. Oh boy. So I think we can use that tool to simplify this then. So rotation matrix, rotates an object, blah blah blah, is more complex than scaling and translating since the whole 3 times 3 upper left is needed to express complex rotation. Yeah, so it seems like you need to do it right 3 times and then like multiply it together. Oh, okay. So we need like a rotation X, rotation Y matrix. Okay, so I think we'll have very simple identity matrices for these, and then we'll do a big boy version. Okay, we got this. So actually, we're going to have so angle in radians, right? Just to be clear. Well, it's always going to be in radians. I don't know, whatever. Right, let's just roll with this. X. Right, so let's just keep that one because that's the identities. Okay. So for the X, it's cosine. So this might be different. Depending on our coordinate system, maybe? I'm not sure. Maybe it's the same. That's a negative one, yeah? So I actually need the HMaths scalar. That'll give me my functions. So for the... So really what we actually want, right, is... let's call it C, right? C and then S. So just be C, S, negative S, C. Okay, so voila. So this next one, which is the y-axis, so that'll just be cosine, negative sine, cosine, sine. Then for the z, that'll just be right. Oh, identity implies no up, does it? Hmm. Right. Hmm. We want to create a matrix from Euler angles. Um, I don't know. Yeah. Um, so you know the whole, you know why people use quaternions, right, for the gimbal lock thing? Do you still get that problem if you because at the end of the day, it has to come from those Euler angles, even when you do quaternions, right? So you avoid the gimbal lock by just using matrices in general, right, rather than a vector, right? Is that correct? Um, yes, what you're saying is we might as well, right? So I might as well just call it rotation x. And then this one just be rotation, and it will just be a simplified version of multiplying these together. Um, maybe. Yeah, that's true. So the scale one is dead basic, right? Um, so that one's just scale x, scale y, scale z, right? Basic, basic, basic. So this one here. So I want to try that tool, right? Because it's quite an impressive tool, and I want to show it off. So it's a SymPy thing. We'll do another. We'll comment all this out, and we'll crap. How do you multi-line comment in Python? Python. Python. Triple quotes. Right. Bob's your uncle. So we'll do this again. To do another one. We'll call this one like RX. It's like a graphics card. Oh. So we should be able to do something like, produce a 3x3. So we want to produce some more symbol. Right, we'll call it cosine. Let's call it, I guess, cosine A. So it'd be like, we'll just call it C, right? In the code. And then let's call that S. And then we should just be able to do, let's go full ham now. Get this in. So we just need to repeat that times. So cosine A. Let's just go through all the cosines. Cosine A. Right, then it's sine A. I've got to do the negative still, but no worries. Then what we should be able to do, right? So negative, right. So this is where it gets pretty cool. So you can you can basically just produce a matrix from all of these. So just do the multipliers, and then you call the simplify. So if you just did the multiply, it might do it in. It will basically print out code which constructs it in this sort of more complicated form, but the simplify obviously will simplify it down to, all the way. So I think, yeah, I think that'd be fine. Doing it that way, I'm not sure. We'll have to give it a go, that's for sure, right? Yeah, we produce M. And then all we have to do is copy this other code. So we can just print M. And what does this do? Code gen print C code. Excellent. So I think we'll just print M as well. And then we'll print the C code. Let's just let's just print out the C code. Oh no, we need a different one. Oh, okay. So print M. So this one here. So we substitute. Oh, so okay. So substituting the names. We don't have to substitute the names here. Yeah, we don't have to substitute any names because I think. Yeah, this was a 2D one that we did with skewing as well. That's what SKX is and SKY. But yeah, also did this inverse thing. I'm not sure what that's about. Because we wanted to produce an inverse vector as well. Wait. No, we called it inverse, wasn't it? Because that was the whole point of the simplifiers. It multiplied it the other way around. Yeah. So produce the inverse matrix. Right, okay. So we're just gonna call it like T, I guess. Or whatever. So let's gen some C code to see how that works. So we should. All different variables, isn't it? We do. That's a very good point. Very good point. Thank you. So CX, X, Y, Y, Z, Z. Very good point. Damn it. Okay. SX, SY, SZ. Okay. So we should get something we can work with. So I think we just did Python 3. Right, you can just execute it like that. Okay, all good. Did we not save it? What's going on? What's going on? Something's definitely fishy. Hey, Captain Chica. How's it going? Welcome back. How you been? How you been? Let's print out the RXs, the RYs and Zs. And let's see what it's all about. Right, so we're seeing them. Right, so that is it simplified. I think this is right. Yeah, that's it. Wait. Yeah, that's it. So we just got to get the column major and row majorness right about this. That's the problem. So what I want to do is actually print out. Wait. Yeah, okay, now I need to make sure the column major row image is better. But as you can see, this is just heavily simplified versus a whole matrix multiplier, which is bloody big. So this just be a big help to making that. What's fishy? My shell. My shell is very fishy. So this would be proper cool. So I just got to get the translation stuff right. So the row major, sorry, the column majorness, right? So when I put it in this way, like these rows or columns, that is the question. I think it ended up producing a row major when we did it last time. So that's why I'm a bit curious. So these are columns, right? Have a think. So right, when I punch these in here, they're meant to go down like that, aren't they? So really I should have put them in the other way around. So I need to kind of transpose them, which means I need to basically just invert the sign thing, and that should be it. So there's not much of an issue. Wait. Yeah, that's it, because they're kind of square, you know. So the thing is the signs just might be different, and that's it. So that'd be pretty cool. So I think I just have to basically move those the other way around, because yeah. Right. That's proper cool. Let's run that and copy the code over. Ash over fish. What's that? What's Ash? You mean Ash Ketchum? The #1 Pokemon trainer? Okay, so we've basically just got to translate this into our format that we've got going on here. So what are we saying? So this is 0. 0 meaning what? Yeah, I think it's just axis. Skeptical. There's a 0. Das ist. That's wrong, isn't it? Surely should have a negative sign in there. Is it cancelling each other out? Something's wrong. Yeah, something's a bit fishy. Oh, they're not the same one, are they? Yeah, makes sense. They're a distance 1 apart. So anyway, what's the one with the 0 in it? Is this guy? Is that always true? The one on the far right's always got 0? Well, yeah, the 2 column. Yeah, this one here. No, there's a sign there on the Y. um. So why has that 2 column got a 0 in it? Does that make any sense? They've all got zeros here. Compared to the RX and the RZ. Ooh. According to this, they're the same. Oh, X and Z. It's better to see it. Yeah, so this one here, the X, you know, I've had to move it the other way around. Right, okay. Different on the Y compared to the X and Z. Hmm. It seems fine to me. I've had to invert the negative or do the negative different because of the column major, row major stuff. But it seems pretty legit to me. Oh, typo. Found it. It's the alignment. I didn't do the alignment, that's why. Right, that'll do it. So, there we go. Although, it's the only one that's not multiplied. Is there another thing that's off? It's the only one that's out on its own, isn't it? Which is this one here. And this one here that's out on its own. No? No, it's not. Because of that. That one's not on its own. That one's not on its own. That one's not on its own. Sorry, that's the one that's on its own. Wait. Ah, so confusing. My brain. My brain. Right, these two are on its own, right? This one and this one. Because no overlap there, no overlap there. Wait, but no, but it's the way the matrix multiplier works, where it will do a... Right, let's make sure I got this right. So these are these guys. Yep. Yeah, they're fine by the looks of it, right? Okay, so we just rerun that. Ugh. Anyway, we can always correct it later if there's an actual problem with it. We'll test it out. Okay, so jobs are good and so all we want to do, right? That's far more simple than doing 3 different identities and then rotating it. Sorry, then doing 3 multipliers, right? So we should just be able to do t dot axis dot, and then we just got to replace these with x, y, z, x, y, z, x, y, z. So now we've just got to produce these cosines and sines. So we'll just do the cx thingy. Yeah, yeah, we'll have a thing exactly what, we need to change this or add different versions. We'll sort it out. Sort that then, I think. You might want to multiply. Hey, you want them composed? No. Damn it. Is that true? Is that true? Yes, you have a right. Oh. Did I get that wrong? Do you might want to rotate them in a different... Right, let's think about that for a moment. So if you rotate along the x-axis first, it will sort of rotate like that. And then on the z. No, it's along the z. The x is coming this way. So it'd be like the x like that. And then the z-axis, right, which can do something like that. So rather you might want it to be, so you'll end up in that position, going left and then going up. Okay, so you go to the left, go up. Right, then that'll point you downwards. Interesting. Right. I guess, yeah, that's right. So this just goes in X, Y, Z order, basically. But yeah, it's interesting to know. Thank you. I'll think about it. Yeah, and also thinking about it, like, so if you rotate around, no, but ideally you want to just define a, you have a rotation in, yeah, radians, yeah. And ideally you'll produce it in the space you're in, like local space, I think. Yeah, but it's something to think about. Right. So that boy there. And then basically what we want to have is a way to pass in, I guess it's in Euler angles, right? We want to pass, we essentially want to do a similar thing, but with translation and scale in there as well. Right, so we'll go and get that sorted out. That's the BFGs. So we'll call this one like big S or big T, and we'll probably need to like add another column. Wait. What major did we do? Yeah, so what end does it go in then? It's arrays of column. Oh, no, no, no. Yeah, yeah. So this needs to be, add another row, goes to the bottom. Okay, so you got T, such translation. Translation just be here, TX, TY, TZ. 1, 1, 0, 0. Let's just get our TX, Ys, and Zs and all that jazz in there. T, YZ. Right. So you got your boys, and then you want to do another one. Does your S's. 0, 0, 0, S. Oh, damn it. Already got an S. Right, SC. SCY. SCX. So we should be able to produce X, Y, like so. Okay, so we just want to multiply that. Now forget the order. Wait, it's scale, rotate, translate. Yeah. SRT. So you want to do S, S, T. And if it's inverse, it's the other way around, right? It would be TRS. So, wait, it doesn't matter which order it is for the rotational scale, right? So ideally, what order do we want? You want the translation. Sorry, the rotation. Do you want it scaled? Yeah, I think it's that order. Yeah, scale first, rotate, translate. Okay, so if we try that. Shoot. Right, you can't multiply a 3 by 4. No worries. We'll do the implicit row. Which we'll just get rid of. If only. Damn it. Right, Bob's your uncle. So let's get rid of the implicit. Wait a minute. I spy a little. I think I got the row major the wrong way around. So it is row major. Shoot. That's fine, we can just fix that up. So I think I need to change the, where does the negates? Right, let's fix this up and then we can apply it, change to the other one that we just did. So in this case, the final 3, or the final 4, you got columns going. So I should have really put my translate here, TX, TY, TZ, and those would have been my columns. Oh, no, 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 it wasn't, it's the right way around. Yeah, it was the right way around. I just had my translate in the wrong place. Because I'm treating this as a column. Right, but it's looking like a row in here. But yeah, it's a column, right. Okay. Let's try that. So it'll be a Z. That's better, because so now they're off the end, right, of each. Okay, good. So that right there is the answer. We just bring it in. And that's how we can take this thing, and rather than making like 5 or 6 matrices and multiplying them together and doing massive code, it can just be something like this, which is proper cool. And I didn't have to fry my brain trying to figure this out. So basically we want to make a right, I forgot this one should have just been a okay. Just transpose the final matrix. Yeah, that's another way of doing it. But they, yeah. T dot axis. Then it'd be something like 0 dot something. So this would be dot x x x x y y y y z z z z, and then the w's just get deleted, right? We have our w's. Then we just got to do this sort of axis 1, 2. Now we don't have a 3. That's a translate. So anyway, translation equal translation. Now I've just got to replace these variables with something like this. So there's those guys all filled in. Now I just need a scale x, scale y. So scale.x, scale.y, scale.z. And there we go. Beautiful, beautiful simplification there. So now we've just got 3 more functions to finish up, and then obviously we've got to test it up, right? So a matrix multiply is actually quite simple to do. Essentially, you just want to produce yeah. Something like this. So column, so we'll do yeah, I guess. Row 0, column 0. Or should we do a column? I'll do it the other way around just for because yeah, some of that. Sorry, 2, 0. Okay. So you can basically do something like this. So this is a matrix 4x4. This is a method you can use to like figure out how do you produce a so really we should call this A and this B. So you have A and B. How do you produce C, basically? That's does. We'll probably need a fair bit of spacing, to be honest. Something like that will do. So what we need to do is you say, you know, you basically take your across, you know, we might not need the spacing. Let's just, yes, you basically take your, you do a dot product between this vector and then this column. So this row, oh, wait a minute. I need to make sure I get the right way around. Wait, so it's no, it's fine whatever way I do it, I think. So you got your yeah, it doesn't matter which way I do it, basically. Okay. Yeah. So your C, let's just call it T then. So you essentially T dot axis 0 dot x is going to be equal, let's get the syntax highlighting to be fine. So essentially, you're going to do, so this is the column and this is the row. So it's column 0, row 0, which is that. So yeah, so to produce this one here, it is A0, there's a dot product, right? So it's multiplied B0 plus B1. I think we could just write it out, right? So it's that times that plus that times that plus that times that plus that times that. And that's what you get, right? So it's yeah. And that'll get you your this one down here, and you repeat that for all of them, basically. So this one, this times that, sorry. Yeah, this times that, plus this times that, plus this times that, and that'll get you this one here. Okay, so, you know, I could just get the tool to simplify it for me. And then I'd have to refactor that, basically. Yeah, I could just get the tool to write it all out. It would be dead easy. That way. The tool. Alright, let's do another one of these boys. I don't know, it takes a bit to actually do it, doesn't it? It might just be easier just to type it out, to be honest. Right, so it's A, but it's also more error prone. Me typing this out this way. Dot x multiplied by b axis. This is where a union would be nicer. Plus, I think as soon as I type out the first one, it might actually be quite easy to do. So then it's column. Then up the column by 1, Z. And then you basically want to add on the translation. So it'd be A dot. No, it's the translations. Yeah, so it's basically the same in it. Dot x. Multiplied by 0. Right, because that's 0, 0, 0, 1. So this multiplied by 0. So you just don't have it on there. So you basically just repeat that. Wait, is there a Z? Okay. So, so this one goes into the Y, this one's going into the Z, and this one's going into the translate. No? Yeah, didn't that kind of a bit. Yeah, then we'll skip this one. Okay. So, this one is actually going down one here to this column. So it'd be A, so all the B's stay the same, right? But all the A's change, and we'll double check the B's when we go over it a second time. So B, so this is going down, so this would be a Y. B dot, yep, that one. Down a row, yeah. This one would then be dot Y. Yep. Dot Y with a dot Z. Going across a column. Two different column vector. Yep. So then this one would just be the same thing, but replace all the dot A's, the dot X's with Z's. Right. Very nice. So that's one. We've just done one column vector there. So we'll do another column vector. So this one. So wait, what have we just done? Yeah, that's the one column vector there. So now we'll go to the next column vector. So it's B. So we've basically just got to replace all the B's with the next column. A should not change X, Y, Z, shouldn't it? Right, let me double check that then. So it was this one here. So this is a column, right? So we've gone down, we've filled in this one here. This one, right, let's just say TA0, TA1, 1x, 1y, TA1. Sorry, what am I doing? 0z. Right, so filling these boys here. So okay, so this one is that times that plus that times that plus that times that plus that times that. So column X, Y, Z, W. I think it's right. Looks right to me. A. Yeah. That's cool. Don't worry. It's bloody confusing. Like, it's easy to make that mistake. Yeah, that's cool. Yeah, the way I've done this axis stuff isn't necessarily the easiest thing to visualize with this. So doing the next one, which would then be essentially this over here. So we're just replacing the B's, right? The B's now just have to be the next column, right? Which is the next axis vector. So we should just have to increment the B zeros to B ones. And everything else stays the same. We might have to put in some translation somewhere. I forgot what it is. I think it's at the end. But anyway, this thing repeats for the next one, right? So the B1s just become B2s, and the B... Right, so something like that, right? Now the final one is the translation. Now for the translation, it's a little bit different, right? Because it's got an implicit one column, which we'll see in a second. So this is going to be translation. Translation there, okay? So the translation sits in the final column of these guys, okay? X, Y, Z, X, Y, Z. So the only time where it matters is when you put down your X, Y, Z in the new in the new matrix you're making, because there's an implicit one at the bottom, right? Because we're doing a 3x4, whatever it's called, right? Sorry, a 4x3. Sorry, yeah, 3x4. Did I do that right? Yeah, 3x4 matrix implicit. 0, 0, 0, 1 row. So this will be 0, 0, 0, 1. 0, 0, 0, 1. So the only time right, let's figure this out. The only time these come into effect is when, wait, this times that times this times that times this times that times this. that. Ooh, yes, the only time the translation comes into effect, right? It never comes into effect when you're doing these three, like vectors, because you know this times that times this times that. Yeah, for this last one here, because it'll be 0. Oh, it should come into effect for these. Crap. Wait a minute. Translation x times. Are we missing these? I think we are. So this times that times this times that times this times that. Oh no, that'll be 0. Yeah, 0, 0. Yeah, 0, 0, 0, 1. Yes, the only times they come into effect is when you are actually producing this final column here, basically. That's the same time they come into effect. So to do that, you've got to do a so it's this one, which is 0, right? So you're timesing it by something, so it's not taken into account. Wait, sorry, ignore that. Sorry. So to produce this one here, so it's this with dot product of that, this times that times this times that plus this times that plus this times that. So this being a 1 field, which means the translation from here just gets added on at the end, right? So in terms of how this works, so it's this one times the translation x, right? So a times translation x. Sorry. B translation x. And then times translation y, translation z. So let's just double check that. So it's a times translation x plus this other a, right, times translation y plus this other a times translation z. And then this x, right, translation x from a times 1, right? Then yeah, you're adding that to it. So you just basically just got to add on the end plus a dot translation x. And I think that's basically it. We should really double check this. It's dead easy to go wrong with this. But that should be the matrix multiply. Bit confusing, but yeah. It's the way it goes. So let's just double check this translation one right, and then we'll pick one of these and we'll just double check it, and then the rest should be fine. Yeah, I was thinking in rows. Yeah, definitely. It's very easy to get that. It's so bloody confusing, this stuff, especially with the column major, row majorness. Ugh, horrendous. So A column 0, row 0. Just to get these last 3 ones here on the C for your new T1. So it's this one times that one, right? Translation X, yes. Column 1, X, yep, times the Y, BY, times column 2, yep. Dot x, that's the row 0, yep. And then it's, oh yeah, so times that with the z, right? X, Y, Z. And then the final bugger, which is the translation column, x times 1. So you just add it on the end, right? Voila. So that all makes sense. That's good. I guess let's just quickly double check this one here, which would be this guy, the one after this one on the right. So it's A's row 1, column 0. That's right, because it's column 0, row 1. Yep. Times by axis B. Column 1, row 0, yes, plus this one, yep, times that one, yep, that makes sense. 2, 1, yep, times 1, 2. Yep. Wait, yeah, times 1, 2, yep. And then we don't do this last one, translation, times 0. Excellent. Right, that's good. That is good. So, next one. Final two, very easy. So, basically, you just do something like this, and you produce a single, like you've got the same number of columns as you do rows. Something like that. I think it's that way around. Something like that, at least. Column vector. Yeah, it is right, isn't it? Oh no, it's the column vector. Ah. Got my back. Thank you, Rasmusko. Appreciate it. Of course it is. Right. Because then you get your translation. So yeah, you get your vector out here. So that's why you've got a 0 or 1 in there, is that right? It's a column vector. Is that right? Because you do this times this, plus that times that, plus that times that, plus that times that. Oh yeah, it is, yeah, because your translation times 1 or 0. And you just add it in the end. Boom. Bob's your uncle. So anyways, there's your sort of your new vector, right? Vector 1 to 2. And the fourth is just implicit row. So ignore it. So it's pretty simple. So you just produce your new result. Let's call it VV. No, probably a terrible name. Let's just call it N. I don't know. So n dot x is going to be equal to just call this n. A bit less confusing. So it's t dot axis 0 dot x See, is this where a row major might be better? I'm not sure. Let's have a think. But anyway, we'll see about it. Maybe it won't be. But anyway, so it's that times plus. So you're going to cross a column, add 1, and then your you're still sticking. So it's that minus times the y in it. And then because it's a vector, we're not doing anything. But if it's a position, we'll take the translation. But we're not taking the translation here. So the rest should be pretty easy. So I'll just do it again. And we'll just change it, so it makes sense. So this time your A should change, right? So it should be rho y. So only the T should change. If the V changes, then we're buggered. So then it's this times that, right? Vx, yep, times this. Sorry, plus this times that. So that'll be a dot y. Yep. And then the same again. This times that. That'll be a y as well. And z, v, perfect. So this will just change to a z. This will change to a z. And this change to a z. Now, we're still, so that is how you would produce just multiplying a vector. But if you wanted to apply the translation to it for a point, you basically just need to add on the final one. So for this x here, you need to say this times 1, and you're adding that on, right? So obviously just adding that. So it's simply you're adding t.translation.x, right? So I'm curious, is this where the, and that should basically be our matrix. I'm curious though, so you still go over all of them you still go over all of them. Yeah, so I guess it's not, I guess it might be able to SIMD it on x86 and stuff like that. Yeah, so I think that's where the rho major comes in, is that right? Oh no, yeah, if it's column major, maybe you can SIMD it. Yeah, the column major is better for doing these sorts of translations, isn't it? Because they're next to each other in memory, and you can technically SIMD it if it's right. Fair play. Right. Very nice. So that means we should be able to do some camera controls. With all of this lovely, lovely maths. Apparently it all compiles. So it should work first time, right? So we've got translation matrix, rotation x, y, and z. We've also got one which combines them all into one. We've got a scale one as well. So I might move the scale one before all of this because it's probably better if we can see those together. Then we've got a way to just produce a transform from translation, rotation, and scale just all in one. So we store these in a separate like properties, if you will. We can then just sort of encode it or compress it, whatever you're going to say it, into it. It's not really compressing, is it? Yeah, you can encode it into a matrix, which makes it obviously really great to operate on when you translate stuff between spaces, right? Because that's what a matrix does. Then you can multiply two matrices together, and then you can also multiply a vector with a matrix and a point. So I should really call this probably vector. Just to make it obvious, right? And this one we'll call point. There's no confusion there. And voila. So I'll just check that in. Thank you, program. So we're gonna still like test this out. So let's just check this in quick. Commit, add transform 3D. So I'll upload that tonight. So in the next stream, what we're going to do is simply test that code out, and then basically, just do a couple of basic vectors and see how they translate. Do some extra multipliers, make sure they work with the translates as well. And then we'll be doing some camera work, getting up to some probably a free cam. Yeah, probably a free. Wait, sorry. Yeah, probably a fly cam. You know what I mean? Flying for the world, and just sort of, have some fun with that. It's nice to include the rotation order in the name of the functions producing the Euler rotations. Interesting. Yeah, that's probably a good way. But then, yeah, have a think about that. Because I don't know, I'm still not exactly sure on where the problem might lie. Yeah, I know you'll get different sort of, I know you get a different one. I had an example where it ended up on the right and then it changed the order, it ended up down, right? But for this, if yeah, maybe we should be explicit in the naming. But I don't know if we'll need the other ones. But yeah, I think you're right though. Or we should at least have a comment where it applies X, Y, Z. Yeah, I don't know if we'll need the other ones because we'll probably design the code around it going in X, Y, Z order, That's definitely a good suggestion. So essentially is the same as rotation X 3D rotation X multiplied. Yeah, maybe I'll just stick a comment in for now. But definitely need to think about that. Thank you for your suggestion though. That is that's good. And then I guess we want to just say like is same as the scale SRT. If only rotation was more simple, but it didn't end up that way. You probably want your around world up and pitch around local right axis. Yeah. Yeah, that makes sense. Right. So if you rotate your So if you did your pitch first, and then your right, that's interesting actually. You might want to do different ones like that, isn't it? Yeah, but in that case it might be fine because you want your pitch. You're all in your pitch. It might be alright. But yeah, when you have like Z involved, it might be more different. Yeah, I'll think about it. It's a good point. Oh, I'm Campaign. Thank you so much for sub, my friend. Appreciate it. Got Prime again. Here's some change. Thank you so much, sir. Appreciate it. Oh, my man. Double the support. Thank you. I hope all is well with you. You doing good, man? Yeah, so for those who don't know, if you want to get access to the code, which I'll upload more tonight, there is a you can subscribe via Twitch or via Ko-Fi, which is a preferred way for me. And as a bit of a thank you, you get access to the code, which is all in Git, right? If you follow the link to the Discord, it tells you all about it and how to get access to the code after you subscribe. But yeah, it works on Windows and Linux. So yeah, all good there. So if you want a world from local, you want the up axis on the left and right axis on the right. Oh, okay. Yeah, so in column, okay, yeah, on the multiply. Right. So you actually want it the other way around. Okay, that's interesting. Right, we might add those then next stream. So you can do that. Yeah, because it is a bit of a bugger. Well, yeah, it'd just be cool to have these like optimized versions that you could do, but it's a bugger. Because then I'm gonna have like, well, no, it's not. Well, yeah, it might be because it's swizzling basically, isn't it? Or in terms of the number of permutations. So you know, three. But it's XYZ, not XYZW. So it's just 9, isn't it? Right, 3 times 3 times 3. They ain't that bad. So there's 9 functions for that, and then there's 9 functions for this guy. Yeah, but it could be cool, right? Well, no, it's not 9 functions. You just want. It's not swizzling, is it? You just want XYZ. Yeah, it might be like 5 or something, right? Because it's like XYZ, XYZ, YZX, and Z, ZXY, and Z. There's just 4, isn't it? There's no other order. No, there is probably another order. Swapping those around as well, and then swapping those around as well. Yeah. So I think there's 6. Wait. Yeah, 6 in total. 6 of those functions, 6 of those. Questionable. Think about it though. Good point. Oh, matrix inverse. Oh, I need one of them as well, innit? Rotation functions, and then we obviously want an inverse. All right. I think we got it. So yeah, I think we'll maybe finish this up and then do some camera work, I guess. But anyway, it's gonna be good. It's gonna be good. Right. I hope everyone has a good start to their week. Oh, Mr. Frogbottom's back on. That's cool. I think you enjoy Mr. Frogbottom. Yeah, have a good start to your work week, guys. I'll see you all on Tuesday. I think I might be starting later on Tuesday, like 8 p.m. GMT. But yeah, check out the Discord on that one, basically, if you're interested on the exact times. But yeah, thank you for coming. Really appreciate it. And yeah, enjoy the work week. Awesome. Yeah, Russ Musker always does. Yep, definitely. Right, catch you later, guys.